From relational to NoSQL databases, most applications use at least one. Many architectures in AWS employ multiple databases of various kinds. In this lesson, we will explore highly available traditional databases on Amazon Relational Database Service, the NoSQL database, Amazon DynamoDB, and data warehousing with Amazon Redshift. You can see here we have a number of interesting options to choose from when it comes to running databases within Amazon Web Services. So just starting from the left, we have the Amazon Relational Database Service. This is a fully managed service that gives us the choice of running a number of different popular databases, such as MySQL, Microsoft SQL Server, Postgres, MariaDB, Oracle, and what we call Amazon Aurora, which is a MySQL compatible database. We have Amazon Elasticache, which is also fully managed. It gives us the option of choosing either Memcached or Redis as in-memory databases. We have the ability to cluster those as well. With Redis clustering, we can achieve up to 3.5 terabytes of in-memory storage. We have Amazon DynamoDB, which is Amazon's NoSQL database. It is inherently highly available, fault-tolerant, very scalable. It is internally replicated across multiple availability zones, and it's also event-driven, so we can tie into events from DynamoDB and feed those into other services such as AWS Lambda. We also have Amazon Redshift, which is a petabyte-scale data warehouse. Redshift is a fork of Postgres. A lot of things that you can do in Postgres, you can do in Redshift. It is, again, inherently fault-tolerant and replicated. It does support encryption, and it's an incredibly powerful data warehouse for a fraction of the cost of traditional data warehouse services. So these are the options that we're going to be talking about in the coming lessons. These are our databases available to us within Amazon Web Services. Okay, so now let's talk about the Amazon Relational Database Service. Before we get into the details of Amazon Relational Database Service, let's just take a look at what it means to run a relational database on your own. Now, in traditional IT, with on-premises solutions, we were responsible for everything from power and cooling to networking. We were responsible for the chassis, for maintaining CPU and memory. We were responsible for installing the operating system, the database itself, for doing backups, and then of course on top of that our SQL queries. In a traditional environment, that's a lot. It requires teams of people and it's very expensive. Now, we could host a relational database system on EC2 if we want, and a lot of customers do that, but we should know what our responsibility is. If we host a relational database on EC2, then Amazon will be responsible for a number of things, from power and cooling all the way up to the CPU and the physical resources of that machine. Once we launch a virtual machine, the operating system is still our responsibility. So from here up, all of these things are still our responsibility. We're responsible for patching and the operating system. We're responsible for the ongoing security of that operating system and the database. So database patches are going to be up to us. Backups are going to be up to us as well. We'll have to either leverage EBS snapshots or some other kind of backup strategy. And then, of course, we're still doing our SQL queries. Now let's compare these two models with what it means to run a relational database within the Amazon Relational Database Service. So within RDS, you can see that our responsibility is much less in this case. So by running a database in RDS, AWS will be responsible for almost everything. that frees us up. It takes away all of that operational burden. We don't have to worry about patching the operating system or patching the database itself. Backups are also automated. That allows us to continue to focus on our application. Data durability is built in. We have the very easy ways of ensuring that our data is replicated, ensuring that our data is backed up. So we have automated backups and automated patches. Because we can copy snapshots across regions very easily, we can achieve geographical diversity in our data very easily. And again, as I've mentioned before, we have the choice of a number of different popular databases, including MySQL, Oracle, Postgres, and another popular database is Amazon Aurora, which is a MySQL compatible service. It's a drop-in replacement for MySQL, which can achieve significant performance improvements over MySQL. We also have the ability with Amazon RDS to create read replicas. These are essentially point-and-click creation of read replicas that can help improve the performance of our applications when we have a lot of read-heavy traffic. So in these cases where we need a relational database, I would highly recommend that you look into running your database on Amazon Relational Database Service, primarily because of this. Amazon handles so much of the behind-the-scenes burden of administration. It really takes a lot of weight off your shoulders and allows you to focus on what you do best, which is optimize queries for your application. So that is the Amazon Relational Database Service. Now let's review data durability within Amazon Relational Database Service. The first thing that we want to talk about is what we call multi-AZ deployments. Again, what we're looking for in any particular application is, one, not only security and durability, but high availability and fault tolerance as well. And leveraging the Relational Database Service gives us this built-in. When we launch an RDS instance, we can optionally choose to launch it as a multi-AZ deployment. So when we do that, the Relational Database Service will place one of the instances, the primary instance, in one subnet or one availability zone, and it will place the secondary standby in a separate subnet and a separate availability zone. That way, we have a resilience not only to the loss of a device, but also to the loss of an entire data center. So if the primary were to fail, for whatever reason, if the underlying physical hardware failed, if there was a network issue, if the availability zone itself were unreachable, then we could fail over to our secondary standby in a matter of minutes. And we do this via DNS. So when we get an RDS instance, what we connect to is a DNS entry, and the Relational Database Service can update the IP address for that entry very quickly with a very low TTL. That way, we continue to connect to that DNS entry. When the IP address updates to our secondary standby, then we will, at that time, connect to that particular instance. So with multi-AZ deployments, we get a very high degree of high availability. We can lower our RTO and RPO to minutes instead of hours or potentially days, as the case may have been in traditional IT. The primary and secondary standby is achieved via synchronous replication. And again, as I've talked about, they are physically distinct. That way we're resilient to the loss of a data center, not just the loss of a machine. So this is considered the best practice for production environments. Another thing that makes the Relational Database Service highly durable is that we can choose to do automated backups. We can set a window during which we want backups to take place. And every day we can have those backups done. These are done in the form of snapshots, very much like EBS volumes. These snapshots are also stored in S3 in kind of this like admin zone that we don't really have direct access to. But we do know that these snapshots being stored in S3 are inherently highly available and durable because S3 is built to leverage all of the availability zones within that particular region. So at any time we can go in and adjust the backup window. We can very easily restore our RDS instance from one of those snapshots or just create a clone for doing some other purpose. We also have the ability to create point-in-time restorations from binary logs. And very much like EBS snapshots, we can copy our backups to other regions to get that geographical diversity. Or if we wanted to recreate that database somewhere else, we could just copy it to another region and then create another RDS instance from that backup. So you can see between multi-AZ deployments and our automated backups being stored in S3, we get a very high degree of durability and high availability and fault tolerance in our databases. And all of this comes really at no extra cost. The ability to do this is included in the cost of the machines. So for production resources, be sure and make use of multi-AZ deployments. Be sure to set your backup window, and that's durability in Amazon Relational Database Service. Now let's review a demo of launching an Amazon RDS instance. Here we are back in the AWS console. From here, I'm going to choose the Services tab up here at the top. I'm going to go to Database and then choose RDS. Now, before we actually launch our RDS instance, there's one thing that we need to do networking-wise first, and that is to create what we call a subnet group. Now, I've already taken the time to modify one of the networks we've created earlier. So I'm going to hit Create Subnet Group. Here I'm going to choose the Data Services VPC. The availability zone I'm going to choose here is 2A. I'm going to choose the subnet that I have there, which is a /24. I'm going to add that one. And I also have another subnet in US East 2B. So I'm going to select that subnet and add that one. So the subnet group will be essentially the group of these two subnets. And by leveraging the group, when we launch our RDS instance, we tell it what group to use. By using the group, now RDS knows what availability zones we want to use, and it will choose the best availability zone from this list in order to place the primary instance. So I'm going to call this one AWS Live Lessons, just for the sake of this demo. I'm going to paste that also here into the description. And of course, you would do this depending on your particular business needs. I'm going to go ahead and create that subnet group. And there we go. Here is our subnet group. So now we're able to choose that when we go to launch our instance. I'm going to go over here to Instances. You can see we don't have any yet. I'm going to click Launch. And from here, we can choose which database we actually want. I'm going to stick with Amazon Aurora for now. You can see here, here's our engine, the Aurora, the MySQL compatible Aurora engine. And now I get to choose which size machine I want. The R3 large would give us 2 CPUs and 15 gigs of RAM. That's plenty for what we're doing here in this demo. I also have the ability to do a multi-AZ deployment by creating a replica in a different zone. So in production environments, I would definitely want to do that. For the sake of the demo, I'm going to say no. Now, the DB instance identifier, you can see here, this is a name that is unique for all DB instances owned by this account in this region. So again, I'm just going to say AWS Live Lessons. The master name, I'm going to just say would be Richard, and the master password would be Richard as well. I'm going to keep that simple, and of course I would use something very secure in a production environment. I'm going to click Next. I guess it's not liking. It needs to be 8 characters. So let's see here. There we go. All right, now we're good. So it needed to be at least 8 characters. I'm going to go ahead and hit Next. I'm going to choose the Data Services VPC. We only have one subnet group, so that comes up as default. We do have the ability to make our databases publicly available if we wanted to, which would give them public IP addresses and make them accessible directly from the internet. Typically, I don't like to do that. I think it's much more secure to leave them accessible only via the private networking. So I'm going to say for this, no, I don't want them to be, this particular instance to be publicly accessible. In the availability zone, I've already specified which 2 availability zones that are available through the subnet group. So by leaving it as no preference, I will be allowing the RDS service to choose which one is best according to supply and demand and the current usage of that particular availability zone. Here I don't have a security group for databases yet, so I'm going to choose Create a New One. We also need to specify some of our database specific information like the database cluster name. Here again, I'm going to put in AWS Live Lessons for that as well. The database port, I'm just going to leave that at 3306. You can see that we have these different parameter groups and option groups that we can specify. I'm going to leave the defaults. If you want to change database parameters, you can do that later by creating a new parameter group, changing those parameters, and then just applying that parameter group to the database. We also have the ability to enable encryption on the database. For this demo, we don't really need that, but if your particular business did need that, then you could just simply choose yes. As far as failover goes, we get to choose that. It says during failover, RDS will promote the replica with the highest priority to primary. So for this, I'm just going to choose tier 0. Now my backup retention, I want that one to be, I think 7 days is plenty, but you could go out all the way up to 35 days as backup retention. But I'm just going to leave it for the sake of this demo at 7 days. Yes, we want it to be monitored. We want it at 1-minute intervals. That's good enough. Yes, we do want auto minor version upgrades. So every night during a maintenance window, which we can specify, I can actually select a window and say, you know what, let's do this on a Sunday night at 1 a.m. UTC. And I want to give the system 1 hour to complete that maintenance. So every night, if there is a minor version patch to be applied to the database software, all of that will be handled for us. All right, we've got all of our options selected. I'm just going to go ahead and hit launch. Looks like there's a problem here. You can see that sometimes some values don't like dashes in the name. So for this one, I'm just going to change that to an underscore. And there we go. You can see that our database is being created. It will take a few minutes. I can go ahead and hit View. And there we go. Here is our Aurora-based Amazon RDS instance in a creating state. You can see here that we've chosen the R3 large instance size. It is not in a multi-AZ deployment. From here, we can see other details, such as the ARN, the subnets that they belong to, the security groups that are applied. And now, in order to connect to this RDS instance, Once this endpoint is available, it'll end up being a DNS endpoint. We can then use that to connect our drivers and our applications. So from here, really all there is to do is wait for this RDS instance to become available. Sometimes it has already happened. We just need to hit the refresh button. And in this case, it's still creating, but now we have our cluster endpoint. So we can click that, we can copy this value, and that's where we will go to actually connect to that Aurora RDS instance. So that is launching an RDS instance within Amazon Relational Database Service. Now let's talk about Amazon DynamoDB. Amazon DynamoDB is Amazon's answer to NoSQL data stores. So again, this is a very different paradigm from relational database services. NoSQL data stores, we call it that because they typically don't use the SQL language, and they typically use just a different paradigm of storing data. Now, the nice thing about Amazon DynamoDB is it's more than fully managed like RDS. With RDS, there are still things we need to do. But with DynamoDB, it's inherently highly available, fault-tolerant, and durable to a very high degree. All of the data will be stored on SSD volumes. It will be replicated across numerous availability zones in that particular region that you're working with. Now, Amazon DynamoDB is designed to achieve single-digit millisecond response times with a consistent lookup no matter how much data you have. One of the interesting things about this particular model is that when we create a DynamoDB table, we provision, at any time we can change this, we provision what kind of read throughput and what kind of write throughput we need for that particular DynamoDB table. I'm using the term table, that's what we call it, but it's perhaps similar to a relational database table, but the difference is that there are no relationships between tables. There's no inherent relationship within the DynamoDB service. We don't do joins like we do in a traditional relational database. If we do need to do that kind of thing, form relationships or joins, we would have to do that within our application. That's pretty true for a lot of NoSQL database technologies. So again, Amazon DynamoDB is inherently highly available, fault-tolerant, and highly durable, with its data being replicated to multiple availability zones, backed by SSD volumes, and designed to achieve a very, very low latency, whether you're storing gigabytes or terabytes worth of data. So let's take a look at data models within Amazon DynamoDB. As I mentioned, we will be creating tables within DynamoDB. Now, even though we're creating tables, it's important to know that there are no joins or relationships. Each table is completely independent. Tables are made up of items, and items are made up of attributes. You can see here that each row in this table is what we would call an item. And then, of course, each item has a primary key, which is required, a unique primary key, and then everything else, all of the other columns, are what we call attributes. It's also an interesting model in that it's schemaless. We don't have to predefine what our columns and data types are going to be before we add them. One item could have one set of attributes, and another item could have a completely different set of attributes. Now, you'll notice here that I've included the name of the column inside each of these fields, and that's because there's no set schema, each attribute will include its name in the total storage for that particular item. We also have the ability to create secondary indexes. Those could be local secondary indexes or global secondary indexes. There is no limit to the size of a table. You could go into the gigabytes, the terabytes, the petabytes if you want to. There is a limit on the particular item. So one item can be no more than 400K, and keep in mind that does include the length of the attribute names. So again, within DynamoDB, we have tables that are comprised of items, and items are comprised of a primary key and attributes. In this particular example, our primary key is a unique name, such as Jane Doe and Bob Smith, the difference between those two being unique. So let's take a closer look at primary keys within Amazon DynamoDB. In our previous example, we used just a simple primary key, which is known as the partition key. Here we have unique values for our primary key. And we call it a partition key because Amazon DynamoDB, being a distributed service, in order to handle the amount of data and the amount of throughput that we might throw at it, the data will be distributed among a number of different nodes or a number of different partitions. And so the Amazon DynamoDB service will determine which partition these items belong to according to the primary key. So that's why they call it a partition key. Now, another option that we have is when we create tables, we could create what we might call a composite key, where we have the primary key is comprised of both the partition key and a sort key. So you'll notice here that while Jane Doe is not unique across the partition key, the combination of Jane Doe and Amy Benson is different, is unique, apart from Jane Doe and Bob Smith. And so it's the combination of these two, the partition and the sort key, that creates what we might call a composite primary key. These types of primary keys are really useful when you want to query for all of Jane Doe's friends and then sort by the sort key. You could also say find all of Jane Doe's friends, but include only the ones that are, less than the letter C or greater than the letter D, so on and so forth. So those are primary keys in Amazon DynamoDB. We either use the partition key, or we use a combination of the partition and the sort key as our primary key. All right, now let's run through a demo of creating a table in Amazon DynamoDB. You can see we're back here in the AWS console. From the services menu item, because I've been to DynamoDB before, you can see that it shows up here in the history. I could also get to it by going over here to Database, DynamoDB. Once we're here, we're seeing the screen because we don't have any tables in the Ohio region yet. So I'm going to go ahead and hit Create Table. I'm going to call the table Movies. And if you recall what we talked about with data models, we need some kind of primary key. For the data that we're going to be working with, we'd want a composite primary key that is the combination of a partition key and a sort key. In this particular case, the partition key will be the year, and we will make that a number. The sort key will be the title, and we'll leave that as a string. From here, we could leave the default settings, or we could uncheck that and make some changes here. You'll see now secondary indexes are something that we could add to add further indexes of our data. These secondary indexes need to be added at the time we create the table. We could also change the provision capacity. It defaults to 5 read and 5 write capacity units. So if you expect your table to be a write-heavy table and not do much reading from it, then you might say you want 50 write capacity units, but only 5 reads. That would be up to you. It can be difficult to determine that up front, so perhaps a good approach is to just make your best educated guess and leverage monitoring over a period of time to see if you need to come back and adjust those capacities. So for now, I'm just going to leave these as 5 and 5. And you can see that at these low capacities, this table should only cost less than $3 a month. I'm going to go ahead and click Create, and that table is now being created. So you can see that DynamoDB makes it really easy to create tables that are inherently highly available, durable, fault-tolerant. We know that the data is going to be replicated, and based on SSD drives, we know that we're going to get predictable, fast performance. So Amazon Web Services has done a really good job of creating a very easy NoSQL service with DynamoDB. So that's it for creating a table in Amazon DynamoDB. Now let's review a demo of scan and query operations within Amazon DynamoDB. Again, we're back at the console. From here, I'm going to click on Services, DynamoDB. From the dashboard, I'm going to click on Tables. And you can see this is the movies table that we created earlier. Now I've taken some time to go ahead and load this table with some data so that we can perform some queries. I'm going to click on the Items tab, and you can see here that we have some data already loaded. Now, let's start with a simple scan. If we just hit Start Search, that will essentially do a scan of the table and pull in data. We could add filters to that. We could say, well, let's filter that based on the year. So if I wanted to enter the year attribute, which is a number, and I could say, well, let's see what movies were done in the year 2000. If I hit Search, there we go. You can see it took it a second or two because it's doing a full table scan. It's not leveraging indexes. So while you can use the scan operation to find records within DynamoDB, we should be aware that they don't use indexes, so they're going to be much slower. If we want to ensure that we're leveraging indexes and getting the fastest response possible, we want to make sure that we do a query operation. Now, in order to use a query operation, we have to know the primary key. In the case where you only are using the partition key, you have to know that exact value in order to find a record. In this particular model, we're using a composite key that is comprised of both the partition and the sort key. So to do a query operation, I'm going to go ahead and remove this filter that we had placed there. I'm going to set the partition key. This is always an equals. Unless we're doing a scan, we can't use anything other than an equals on the partition key. So I'm going to put in the year 2000 for that one. And then for the sort key, you can see that these values are strings. We then have some control over how we query that particular attribute or that particular key. So we could do something like, let's say that we want to look for something called one of my favorite movies, The Matrix. If we know it exactly, we could go ahead and hit Start Search. And let's see, that didn't give it to us. Let's try that again. Maybe I misspelled it. It should be, let's try begins with the, and see if that'll give it. There we go. So you can see how fast that came back. Oh, I have the wrong date. I forgot. The Matrix didn't come out in the year 2000. It came out in 1999. So let's try that. Start search. There we go. And you can see how fast that came back. And it came back in milliseconds because we were using indexes in the query. So there it is. There's the matrix. And then we could pull, here are all of our attributes. So we could look at that and go, the title, the year, here's all of the information about that movie. Now, if we wanted to, we could also say, let's try this. Let's look for movies that came out in 1999 and all movies that are less than Z. So essentially, well, let's do this. Between the A and Z. And we're going to sort them ascending, and of course you can guess what we'll sort on. Of course we will sort on the sort key. That's what it's for. If we hit search, and there we go. We get all of the movies in the year 1999 sorted by title A to Z. We could choose descending and do that again, and very quickly we get the same list back in reverse order. So those are scan and query operations. Again, scanning does a full table scan. It does not leverage indexes, so it's going to be much slower, but you do have a little more control over how you query the data. If you want to ensure that you're getting the fastest response possible, be sure to use query operations leveraging the primary key index. And of course, if you have placed secondary indexes, you could leverage those as well. So those are scan and query operations within Amazon DynamoDB. Let's talk about Amazon Elasticache. Amazon Elasticache, very much like Amazon RDS, is a fully managed service. Things like minor patch updates, backups, operating system patches are all done for us automatically behind the scenes. With Amazon Elasticache, we have two choices. We have Redis, which is an in-memory database. It supports multiple data types. It's also backed to disk, so we do have the ability to stop that and recover if we need to. Memcache is the other choice, which is an in-memory simple key value store. It is not backed to disk, so we don't have the ability to recover. If there was a complete loss of the Memcache cluster, then we wouldn't have the ability to restore. So that's why both of these systems do support clustering, so that if we lose one instance, we still have our data in other instances. So again, Amazon Elasticache, fully managed service, just like RDS, and it gives us access to in-memory databases or in-memory key value stores. Just one of the possible use cases is to put this in front of, let's say, a database where you might have a read-heavy operations that are, maybe your queries are getting slow in certain conditions, and you want to take the data from that query and store it here in perhaps Redis or Memcache in memory, so that the next time that query needs to be ran, you can just pull it very quickly out of memory and deliver it back to the user rather than replaying that SQL query. So that is Amazon Elasticache. All right, so let's talk about Amazon Redshift. Amazon Redshift is Amazon's petabyte scale data warehouse. Just like RDS, it's fully managed. It is based on a fork of Postgres 802. Very much so, as a result, it's also SQL compliant. So you can connect to your Redshift cluster with all of the drivers that you're used to using, JDBC and ODBC drivers, and run SQL queries that you have been running in Postgres. Now, under the hood, Redshift is a clustered service, so it makes use of multiple nodes. You get to choose how many nodes you want, and based on those number of nodes will also determine the amount of storage that your cluster will receive. And Redshift uses some really interesting technologies developed by Amazon to run these queries in parallel across those nodes, across very large data sets. So these are ideal for OLAP and BI applications. So Amazon Redshift fulfills a really interesting place within Amazon Web Services, providing analytics and business intelligence at a vast amount of scale. So again, Amazon Redshift, fully managed, just like RDS, is a petabyte scale data warehouse. Now let's review another use case of databases for an e-commerce application. In this example, we have an e-commerce application architected to be highly available and fault tolerant by leveraging, one, the elastic load balancer, which we'll talk more about later, and multiple EC2 instances spread across multiple availability zones. That way, now we have a resilience not only to the loss of one of these machines, but also to the loss of an availability zone or a data center. Our e-commerce application will read from an RDS read replica, which is really easy to create. It's essentially just a few clicks of the mouse and you have a read replica in place. So by pulling our reads from our read replica, we can reduce the load on our primary and increase performance. All of our writes will be done to our primary RDS instance. We have RDS deployed in what we call a multi-AZ deployment, where the Amazon Relational Database Service handles the creation and management of the secondary standby for us. Amazon RDS also handles the failover in the case that our RDS primary is unreachable. Here in our RDS, this could be MySQL, it could be Microsoft SQL Server, Oracle, Postgres, a number of other options, Amazon Aurora. We are going to store our user accounts, our product catalog, orders, and perhaps a number of other things. Now, our category pages and related product pages, sometimes those take a little bit longer to render than we would like. Those pages tend to be a little bit slower, so what we're going to do is we're going to render those and store the output here in Elasticache. Now, this could be Redis, this could be Memcache, but we're going to store that here in memory and refresh them perhaps every 5 to 10 minutes. These are pages that don't necessarily change very often, so we can get away with caching those for some period of time. By leveraging Elasticache, we can further increase the performance of our application. Now, we're going to use DynamoDB for other types of data, some of it being marketing campaign events. So we have marketing campaigns out there in blogs, in news articles, in paid placement, and we are sending people from that campaign back to a particular landing page on the site, and we want to track where those people came from, when they got there, and then where they went from there. We're also recording the affiliate tracking. So we have marketing affiliates, members of the site that are placing some type of a link on their own blog or whatever, and we want to track when users come through that link and they come back to the site and purchase something, we want to associate that transaction with our affiliate. So we're going to record all of those affiliate link backs here in DynamoDB. We might also want to record the view history of a particular user so that we can very quickly retrieve a history of what they've looked at over time, also the things that they've searched for. We can use the product view history and search history to later send marketing emails to that user. Hey, we noticed that you've been looking at these things. Perhaps you might be interested in something else. Or, hey, this thing that you looked at is now on sale. Those kinds of things. We will also use DynamoDB for our shopping carts as well. From there, we will take all of the information stored in DynamoDB, all of this, and we'll take everything stored in our relational database, and we will copy all of that into Redshift so that we can perform very complex business intelligence queries on the entire set of data and to be able to determine those kinds of relationships. You know, typical trends, like what are people doing over time? We want to use Redshift to be able to understand conversion rates. You know, as people come in from campaign events, as they come in through affiliate tracking, as they come in through marketing emails, how much of that ends up converting a customer into actually buying something. We also want to track our campaign performance. We want to use Redshift to determine how much we actually pay our affiliates every month. So you can see through this example, this is just one example of a myriad ways that we can use databases within Amazon Web Services. And you can see that each database performs a very specific function. There's no one-size-fits-all approach to databases within Amazon Web Services. So most applications, many applications anyway, will make use of at least 2 or 3 different types of databases. The beautiful thing about these services is that they're just so incredibly easy to put in place. The barrier to entry is so low, the price is so low, that it makes it really easy for anyone from a 2-person startup to medium-sized businesses to Fortune 500s. It really enables us to go to market so much faster by having all of the low-level infrastructure-related burdens handled for us. That way we can focus on our application. We can focus on our business intelligence, further adding value to our application. So that's, again, just one example of using databases for an e-commerce solution in Amazon Web Services. Big data and real-time analytics are hot topics these days, but not necessarily a simple or easy thing to jump into. In this lesson, we will explore the exciting technologies AWS has to offer, such as Amazon Kinesis and Amazon Elastic MapReduce. We'll also review tools that make it easy to move data from one place to another, as well as a use case highlighting business intelligence by making use of a number of various services. Let's talk about real-time stream processing with Amazon Kinesis. Before we get into the details of the Amazon Kinesis service, let's first review a use case. I think it helps to understand a real-world problem when it comes to real-time stream processing. So let's take the example of a very popular pizza chain around the world. So currently, this particular pizza chain would have somewhere around 11,000 locations, nearly 40,000 delivery drivers. Now, with these 11,000 locations, each having perhaps multiple devices, maybe laptops, tablets, at different stations, at the dough station, at the oven, so on and so forth. We have delivery drivers that each have mobile devices. And then, of course, we have millions of customers to whom we serve more than 1.5 million pizzas per day. So we have a lot of people and a lot of data to track. Now, what we have is an antiquated ordering system built using SOAP and old school technologies out of the 90s, and we want to update that. We want to bring it into the modern era, host it in the cloud, and really make this much more of a modern real-time system. Currently, we're leveraging daily, weekly, and monthly reports, but we want to get near real time. We want to be able to see what's going on now. We don't want to be responding to what happened yesterday or the week before. We want to be able to respond to situations much more quickly. Now, currently, customers have no insight into what's happening with their pizza. You know, where is my pizza? What stage is it in? Why am I waiting so long? So we want to be able to give our customers some insight into, you know, hey, your pizza just went into the oven. Your pizza just went into the box. Your pizza is now in the car and on the road. So currently we have absolutely no way of doing that, but we're going to architect a solution to add that ability. So our goals over the next couple of years will be to add an additional 5,000 locations, an additional 10,000 drivers, and we want to, by then, be serving more than 2 million pizzas per day. So you can see here, we will be increasing the amount of data that we're tracking significantly. We also want to enable our customers to order with their mobile device. We want to allow them to pay with their mobile device. We want to allow our drivers to track, you know, where they are, when they've delivered it with their mobile device. We want to enable different stations in the pizza making process the ability to check in via some type of a mobile device like a tablet. And then we want the ability to do real-time reporting, right? We want not just across the board, but per location. We want to be able to zoom into a particular store and see what's happening with that particular pizza shop in real time. We want to be able to see, kind of aggregate pizza shops by region, by country. And of course, as I mentioned, we want to be able to see what's happening per pizza in the step along the way. And we want to enable mobile push notifications so that we can alert our customers, hey, your pizza is on its way, or hey, your pizza was delivered. First, let's look at our API. Again, we have pizza locations, we have customers and employees and drivers sending data with their mobile devices, with their desktops and laptops. So we have millions of events coming in to our API, which is built in a highly available, fault-tolerant way using the elastic load balancer, leveraging multiple EC2 instances in multiple availability zones. So we get high availability, we get the ability to handle requests at a high scale, but what we're lacking here with a normal traditional API is the ability to process real-time data. Now, yes, these EC2 instances, being a part of this API, can ingest all of these events. It can write it to a database. It can write it to RDS, to DynamoDB. It could write it to Cassandra, to MongoDB. But still, we're lacking the ability to actually do any kind of meaningful analytics on this data as it comes in real time. And the problem is that as events are coming in, they are being distributed among our EC2 instances. So perhaps an event on, Joe's Pizza first comes in here, and then a little bit later, Joe's Pizza goes into the oven, so another event comes in and it goes to this machine. Later, Joe's Pizza goes into the car to be delivered, and that event goes to another machine. And so the problem here with these instances trying to do any kind of real-time data processing is that each of these instances are receiving a subset of the data. They are not receiving all of the data for that particular pizza. No one machine is receiving all of the data for that particular pizza location or that particular region. And so that's where Kinesis comes in. That's how Kinesis can help. So we're going to augment our solution by adding a Kinesis stream. Again, we have this incoming stream of raw event data coming from our employees, from management, from our customers and delivery drivers, these millions and millions of events coming in a live stream, and we're going to accept those requests via our highly available application running on EC2, but instead of just simply recording those to a database, we're going to also send those records, those events, we're going to put them to a Kinesis stream. Now, what Kinesis does, it will divide that stream into what we call shards, where when we do this put action and we put that record into a Kinesis stream, we specify a partition key, something unique that sets, Joe's Pizza apart from Sally's Pizza. We set store number 1 apart from store number 3. And so Kinesis will automatically divide that data into these shards based on the partition key. Then we can have another application called consumers that each consumer will pull from one shard. That way, this particular EC2 instance can now get all of the data associated with a particular store. And now it receives the whole of the data, the full data set of a particular store. Or an EC2 instance would receive, in the case where we're tracking events and data based on one pizza, then we want this particular machine to receive the full data set about that one pizza. So that's how Kinesis helps, by dividing data into shards and ensuring that our application that is performing this real-time, analytics can receive the full data set of our groupings, however it is that we group things, whether it's by pizza or by store or by region, and so on and so forth. So that's part one of real-time stream processing with Amazon Kinesis. Now let's talk about part two of real-time stream processing with Amazon Kinesis. So as we've talked about in part one, Kinesis is a service that helps us to divide a large amount of data in real time into usable shards, manageable shards, so that EC2 instances or even AWS Lambda can read from that particular shard and ensure that whether we're looking at one store or one pizza, we're going to receive the entire data set for that pizza or for that store. So we can ensure that a record gets to the right shard by the partition key. Now, the partition key does not need to be unique per record. So in this case, perhaps every event that happens on a particular store would have store number one like this as its partition key. This is just one example of virtually limitless ways of achieving something for your particular business. So here, our partition key might be, pizza 2, or pizza 4. And so Kinesis is responsible for grouping all of the like partitions into the right shards. Very much like relational database service or Amazon DynamoDB, Kinesis is also fully managed. There's nothing we need to do other than to say, hey, I want a Kinesis stream. As we see our traffic start to increase, as we see that we're starting to handle more and more orders and more events, then we can very easily scale Kinesis simply by adding shards. So each shard can handle 1,000 put requests per shard per second. So as we start to see more and more data come in, then we can just very easily, with a few clicks of the mouse or a simple CLI command, we could add shards to enable our Kinesis stream to handle that increase in traffic. Now, by default, records are stored for 24 hours, but we do have the ability to push that out up to 7 days. In some situations, the order of messages might be important, so that's one of the nice features of Kinesis, that it does maintain message order, and it gives us the ability to collect terabytes or more per hour. It's an incredibly scalable and resilient service. We also have available to us the Kinesis client library that really eases the development of applications reading from our Kinesis stream. Another really great thing about the Kinesis service is that multiple applications can read from the same stream, even from the same shards within that stream. And that's what makes it so powerful. So in a microservices architecture, what we don't want is a monolith that tries to do everything. That just becomes unmanageable. So what's a whole lot easier to maintain in the long run, what's a lot easier to develop, especially when you're dealing with a team of developers, are applications that are purpose-built, applications that do one thing and they do that one thing really well. So we might have one application that is dedicated to aggregating these records and storing them like the raw events in S3. And that's perhaps all that application does. It simply takes the events out of the stream, it writes them to flat files, and it stores them in S3. We might have another application that does real-time metric extraction and or sliding window analysis, and then storing perhaps we have our windows at 1 minute. So every 1 minute, this machine is collecting data and doing totals and averages and whatever other kinds of aggregate functions we can think of, and storing those in DynamoDB so that yet another application can pull data out of our DynamoDB table and display real-time dashboards. So perhaps it's from this DynamoDB table that we can display to management what's happening in real time per store. Perhaps as our customers, log into their account or open their mobile application, data about where their pizza is in this process is being pulled from an item in this DynamoDB table. We might have another application doing event processing, pulling things out, and simply when they see the event that denotes a pizza going into an oven, then perhaps the one application will send a notification based on that. Kinesis makes it really easy to integrate with other data stores. So you can see that Amazon Kinesis is an amazing service that really eases the development of processing vast amounts of data in real time. So that is real-time stream processing with Amazon Kinesis. Let's talk about big data with Amazon Elastic MapReduce. Amazon Elastic MapReduce is another amazing service based on the Hadoop framework, which is an open source software published by the Apache Foundation. So we can run Hadoop, we can run Spark or Presto or HBase as well. And the Elastic MapReduce service gives us very easy access to potentially thousands of nodes, a very, very powerful processing cluster that enables us to process an incredible amount of data, terabytes or more of data very easily, very quickly. So we can pull data from just about anywhere. We can write data to just about anywhere. A common approach is to, perhaps we're storing log files, some type of a log file, maybe it's records of just raw events in S3, and perhaps we have terabytes worth of events here, and we can pull that in to Elastic MapReduce. We have what we call a master node here that will divide that data up into manageable chunks and send that off to the core or task nodes, as we call them. So these nodes are the nodes that actually do the heavy lifting, do the work, and then report their findings back to the master node. And the master node is coordinating all of the work between these worker nodes or task nodes. We can provision just one or up to thousands of instances, again, very, very easily if we need to. Now, again, if we recall what we talked about in the billing lesson, these types of nodes would be a really great opportunity to use spot instances. A lot of customers use that because the work that these are doing could be potentially short, it could be potentially interrupted and saved so that it can come back and pick up where it left off later. So spot instances here is a really great way to save money in your batch processing. Amazon Elastic MapReduce is a very ideal service for doing these kinds of very data-intensive applications. Perhaps we want to do some data mining. We want to do scientific simulations like weather modeling. We want to do genomics. Whatever it is, when we're dealing with terabytes or petabytes worth of data and we have very complex questions that we're trying to answer, Elastic MapReduce is a really great tool for that. And you can see it integrates very easily with other services by allowing us to read data from, again, just about anywhere. S3, DynamoDB, we can pull data from DynamoDB tables and then write them to yet another DynamoDB table, or we can pull them from just about any source and write them to Redshift. So you can see that Amazon Elastic MapReduce is an incredibly powerful, incredibly flexible tool to use for those big data applications. So that is big data with Amazon Elastic MapReduce. Now let's talk about AWS Data Pipeline. The AWS Data Pipeline is another very useful service that helps us move data from one service to another. Perhaps we have data in S3 that we want to get into Redshift. or we have data in DynamoDB that we want to copy into RDS, but they're different data types. They're stored in different ways, so we need to transform that data from one data type to another data type, and Data Pipeline can do that as well. So again, it helps us move data between various services, including those outside of Amazon Web Services, such as on-premises. Maybe we have data stored in some type of a local database, perhaps it's Oracle or an on-premises SQL server, and we want to run queries on that data and then store that data somewhere else within AWS. So we can use Data Pipeline to execute SQL queries and then take the result of that and store it somewhere. We can use Data Pipeline to execute custom applications. So perhaps we have custom applications running on EC2 that pull data from somewhere or generate some kind of data from an external API, does whatever processing that it does, and then Data Pipeline can facilitate the moving of that data from our application to perhaps Redshift or back to DynamoDB. We also get the ability to schedule these operations. So perhaps we want to every day move data from a DynamoDB daily table to Redshift and then perform daily aggregates and the like. It does have built-in error handling, and then of course the execution logs of whatever happened will be stored in S3 so that we can go back and analyze. Perhaps something went wrong, we can go back and look and do our troubleshooting from there, or we can just look at those logs and see, yes, indeed, our data was pulled from DynamoDB, yes, it was written into Redshift. So you can see that AWS Data Pipeline is yet another very powerful, very flexible tool that can help us move data from one place to another. It can help us transform that data from one data type to another. And so it's a very useful service, and that is AWS Data Pipeline. Now let's review a use case where we perform business intelligence on a video subscription service. In this example, we have a video subscription service, something similar to Netflix, where our customers are out there watching videos on their laptops, their desktops, their mobile devices, and as they're watching videos, as they're pressing play, as they are pressing pause, as they're scrubbing forward or backward or replaying or rewatching or favoriting a particular section of the video or leaving comments, all of these events are coming in to our Kinesis stream. And from that stream, we have a number of different applications that are doing things like sliding window analysis. You know, how many videos are actively being played right now? What videos are being played right now? What categories are being watched right now? As new users actually sign up, we want to be able to see how many users actually became new users in the last minute or the last hour. So we're doing these sliding window analyses, and those are being stored in DynamoDB. We have another application that is just taking the raw event messages, aggregating those per hour or per day, and storing those files in Amazon S3. From there, we have our user account information, we have video metadata being stored in the Amazon RDS using Amazon Aurora database, which again is a MySQL compatible database, but gives us a much greater performance over stock MySQL. We also have our finance and accounting team is using SQL Server on Amazon RDS to track how much we spend on marketing campaigns, how much we spend to produce video content. And so you can see that we have data stored in a lot of different areas. Each area, each particular database, whether it be RDS, Amazon Aurora, or SQL Server, or DynamoDB, they are serving a very particular function. But it still means that we have data in a lot of different areas. So we're going to use AWS Data Pipeline to run queries on these various databases. We're going to pull in information about user accounts. We're going to pull in information about videos. We're going to pull in information about all of our financials. We're going to aggregate all of that data and store it over here in Amazon Redshift. We're also going to take the data from these sliding windows. We're going to leverage AWS Data Pipeline to pull data from DynamoDB and transfer it over to Redshift as well. From here, now we can use our business intelligence software to run much more complex queries across the entire data set that would have normally been very difficult because they were in all of these various disparate databases. But now that all of that data is in one cluster, we can leverage the massive parallel processing power of Amazon Redshift to answer some very complex questions. We could also, if we wanted to retroactively go back and ask questions that we weren't asking at the time the data was coming in, we could go back, pull these raw log files out of S3, load them into Amazon Elastic MapReduce, leveraging the power of thousands of nodes running in parallel to further process those logs and store those results also in Redshift. So with all of this data being pulled in and aggregated into Redshift, then we can start to get a sense of what's happening in the big picture. We want to start to understand things like user engagement per video. We want to understand how well a particular series is doing versus other series. How much are people interacting with? How much of a video are people watching? We want to see user engagement, again, per video, per series, per category, and so on. We want to understand our conversion rates. As we're spending money on marketing campaigns, people are coming back to the site as a result, but how many of those people come back? How many of the people that come back, how many of those actually become customers? So what are our conversion rates? We can answer those questions given all of this data from our user accounts, given the data that we spend on marketing. We can answer those questions. We can also figure out how much we spend per customer acquisition. How much does it actually cost us to acquire new customers? We also can look at our user accounts and the money that we're spending and determine what are our user churn rates. This month versus last month, how many users signed up versus how many users canceled their account. So again, you can see this is just one more example of the many, many ways that we could possibly put all of these various services to use to analyze a very large amount of data very easily within Amazon Web Services. So that is just one example of video subscription service business intelligence leveraging multiple services in Amazon Web Services. It's one thing to develop an application, quite another to deploy, and yet another to create and manage the underlying infrastructure. To do so in traditional environments can be time-consuming and expensive on numerous levels. In this lesson, we will discuss a number of AWS offerings that really help developers get to market faster and relieve operational burdens. Now let's talk about monitoring with Amazon CloudWatch. Amazon CloudWatch is the service that we can use to collect metrics from our resources such as our EC2 instances, our Elastic Load Balancers, EBS volumes, our RDS instances, DynamoDB tables, and more. Now, Amazon CloudWatch is not, I wouldn't consider it to be a complete monitoring solution. Ultimately, Amazon CloudWatch, we could call it a metrics repository. It's for collecting metrics, and it will store those metrics for up to 2 weeks. That's really important to know because if you want to be able to compare the performance of your applications, your volumes, your databases this week versus this week last year, then you're going to need to tie into the Amazon CloudWatch API, leverage those command line tools, leverage the SDK, or some third-party service like New Relic or Datadog or CopperEgg, Nagios, the list goes on. You want to leverage something that can tie into the Amazon API, pull those metrics out and store them for a longer period of time. Now, each particular service, such as EC2, ELB, Amazon Elastic Block Store, RDS, so on and so forth, each service will get its own unique collection of metrics. We do have the ability to publish custom metrics to Amazon CloudWatch, and of course, by doing so, we will pay a certain fee per metric. One example might be that we have an agent running on our EC2 instances that records the number of processes running. Perhaps your bottleneck is not necessarily CPU or memory, but let's say we're running a PHP application, and perhaps you found that the bottleneck is not on CPU or memory, but rather on the number of processes that are running. So you could write an application that would regularly monitor and count the number of PHP processes that are running, and then report those to Amazon CloudWatch as a custom metric. And then from there, you could do things. You could create alarms and different things from that custom metric. You could have application level metrics as well if you wanted to. Now, as an example, when we look at the type of metrics that we get out of the box, one example of EC2 is that the default is going to be at a 5-minute interval. If we wanted more detailed than that, we can pay a certain amount per instance to get access to 1-minute intervals. It's important to know that EC2 is only reporting to CloudWatch those metrics that are available to the hypervisor, such as CPU utilization, network I/O, disk I/O. But while the hypervisor knows how much memory an EC2 instance might have in total, it has no way of knowing exactly how that memory is used. So out of the box, we don't get memory metrics from EC2. If we wanted those on an EC2 instance, we would have to write some kind of application that would measure memory, system versus user and so forth, swap and all that, and then record those back to Amazon CloudWatch as custom metrics. So out of the box, EC2 does not get memory metrics reported to CloudWatch. With the Elastic Load Balancer, in order for us to be able to scale rapidly, and we're going to talk about auto-scaling and how that plays with the Elastic Load Balancer here coming up, but for now, if we need to scale, we need to scale quickly. 5 minutes is too long to wait. And so the ELB comes with a default of a 1-minute interval, and again, it has its own collection such as the number of requests, the number of HTTP 200 responses, 300, 400, and 500 responses, back-end connection errors, things like that. RDS does come with memory usage. It also measures the number of connections, how the disk is being used, so on and so forth. With DynamoDB, we get metrics such as the number of reads and the number of writes that we're doing, among others. Now, again, Amazon CloudWatch being a metrics repository, that is very useful, but what's even more useful is the ability to create alarms based on those metrics. So an alarm is simply something that happens when it's something that's triggered when a particular threshold is breached. An example of that is, let's say that we have an EC2 instance with some application running, and we want to be alerted, notified, when the CPU utilization is above 80% for essentially more than 2 minutes. Or the way that we structure it in Amazon CloudWatch is to say 2 periods of 1 minute. Now, once that alarm happens, it doesn't necessarily mean that something's wrong. An alarm doesn't necessarily signal an emergency. It just means that the CPU utilization is above 80%. Whether that's an emergency or whether something is wrong will be up to you to determine. Just because we call it an alarm doesn't mean that something's wrong. It just means that a particular metric went over or under whatever threshold that we set. From there, we can do a number of different things. One possible thing we could do is to send that alarm notification out to a simple notification service topic. And we'll talk more about this service later on. But for now, we'll take this alarm into the simple notification service, which will publish that notification out to different subscriptions that we have applied to that particular topic. In this particular example, we're going to subscribe to this topic by way of email and a service called PagerDuty. And then PagerDuty will be responsible for sending that alert to a cell phone and then escalating that to various team members if someone doesn't respond in a particular period of time. Now, I've mentioned this before that there are limits within Amazon Web Services. We do get up to 5,000 alarms per account, but it's also important to know that some limits can be lifted simply by sending a ticket into support and asking for that limit to be lifted. Amazon, a lot of their services have soft limits in place just to control usage, just to protect those resources from, runaway scripts or novice users who aren't, fully aware of what they're doing. One more point to make here is that Amazon CloudWatch alarms can exist in one of three possible states. The OK state means that. It means that everything is okay. In the case of this alarm here, the CPU utilization is less than 80%, and it has been for some time. An alarm state, again, it doesn't necessarily mean that something's wrong. It just means that our metric has been above or below the threshold that we've set for whatever period we defined. And then, of course, insufficient data just means that we don't know yet. So in the case of this alarm, when we first create that alarm, in the very first minute and 59 seconds, this alarm will exist in an insufficient data because 2 minutes would not have gone by yet. Now, it's also important to know that some resources don't report a value of 0. So if they reach a value of 0, like the simple queue service, for example, when the message count reaches 0, it won't report that. And so you could end up with an insufficient data from those sources that don't report 0 values. So in some cases, insufficient data would essentially be the same as OK. And that is Amazon CloudWatch and Amazon CloudWatch alarms. Now let's talk about log collection with Amazon CloudWatch logs. With Amazon CloudWatch logs, we have the ability to stream our logs in real time to the Amazon CloudWatch logs service. So the way that this works is that we install the Amazon CloudWatch logs agent on our EC2 instances. We configure it to watch whatever log files are being written to disk. It could be Apache or Nginx log files. It could be our application. Whatever application is writing log files, the Amazon CloudWatch log agent will essentially follow that log file. Whatever goes into it will be captured and streamed in real time to the Amazon CloudWatch logs service. By default, Amazon CloudWatch logs will retain those log files indefinitely. We can shorten that if we wanted to. Perhaps we only need to store certain things for a week. We could also have Amazon CloudWatch logs archive those off to S3 so that we can very easily, as we've seen, pull those into Elastic MapReduce. We could pull them into a data pipeline and transform and do other things with them. We can also very easily stream those into Amazon Elasticsearch, which is very much like RDS, is a fully managed Elasticsearch service. And it's also worth noting that Amazon Elasticsearch includes, for those of us who might be familiar, it includes Kibana, which is a very nice and very powerful UI tool for searching and performing analytics against records stored in Elasticsearch. So this particular service is incredibly powerful and rich. It enables us to capture these log files and very easily get them into a place where we can do more with them. It's very important that, especially in a distributed environment where you have potentially dozens to hundreds of EC2 instances, instead of all of them being responsible for packaging their log files, writing scripts to get their log files to various places, it's a whole lot easier and simpler just to install the CloudWatch Logs agent and allow that to handle the collection and aggregation of logs for you. Now, another thing that we can do within CloudWatch Logs is we can search and filter that log data. So we do have a very specific syntax, and I would encourage you to, again, make the documentation your best friend. I've been using Amazon Web Services for 7 years, just about every day over the last 7 years, and I still go to the documentation just because it's so much information to remember. So you can search JSON. A lot of the applications that I work with being written in Node.js leverage JSON and store our logs in JSON. And so yes, you can search on those fields. We can create what we call subscription filters. So not only can we go in and just type something like this, error exception, in the search field, which would match messages like these, we could also turn those searches into what we call subscription filters, so that as these logs come in real time, each log message is compared against that subscription filter, and messages that pass through, messages that match that filter, could then be streamed into Kinesis. We could stream them into AWS Lambda and do further processing from there. We could also create metric filters so that, for example, here, if we created a metric filter based on this here, every time we see the word error or the word exception, we could count that and say +1, +1. And then this would end up counting as a custom metric within Amazon CloudWatch. From that, we could create alarms. So we might want to count, the number of 404s. In the case of a web server, we might want to count the number of bytes that were transferred by that web server per request or over a period of time. As our applications write their log files, we might want to count the customer conversions. Every time a customer closes a shopping cart due to a sale, we add that log message. We can configure our filter patterns to search for that and then count the number of sales that are happening. So you can see between Amazon CloudWatch Alarms, and Amazon CloudWatch Logs, we have a very rich and powerful system for collecting metrics and for collecting logs, and that is Amazon CloudWatch Logs. Here we'll review infrastructure as code with AWS CloudFormation. One of the most powerful things, and I think one of the things that really sets Amazon Web Services apart from other providers, is the ability to think of our infrastructure as code, to configure our infrastructure by writing not only scripts, but writing things like CloudFormation templates. So CloudFormation is a solution to a particular problem, and that is that our architectures can often be very complex. There are often a lot of moving parts. When you really zoom out and look, and you'll see that we have virtual private clouds, we have subnets and route tables and network access control lists, security groups, EC2 instances of various types and various sizes, doing various different jobs. We have databases and DynamoDB tables. The list goes on. There are so many resources that need to be created and managed, and doing these manually are challenging because if we architect something and we draw it out in a diagram, we have to know that it's reliable. We have to know that it was created exactly the way that we designed it. And then, of course, comes the issue of reproducibility. If we want to take that environment, that particular architecture, and create it in a development, a testing, a staging, a production environment, we're looking at doing that manually, not once, but 2, 3, 4 times or more. What if we wanted to take that architecture and roll it out to multiple regions so that we can serve a broader audience? Again, it's one thing to do it once, it's quite another to do it 2, 3, 4 or more times. And then, of course, comes the issue of documentation. By having all of this handled by a template, by a script, then the template or script becomes somewhat self-documenting. Now, yes, we can do these things with just scripts. We could do them with Bash shell scripts, leveraging the Amazon command line tools. We could do them with a programming language such as Python, leveraging the Bodo libraries. But the challenges with scripts could be dependencies and parallelization. We need to know that certain resources have to come first. Before you launch an EC2 instance into a VPC, you first have to create a subnet. And before you create a subnet, you have to create the VPC. So your scripts need to know the appropriate order in which things need to be created. So the solution to all of that, the solution to the challenges of a manual process, the challenges of human error factors, the solution to the challenges with scripts is to automate with AWS CloudFormation. CloudFormation gives us the ability to write what we call templates, which are just JSON formatted text files that we can and should put into source control. We then upload those to the CloudFormation engine, which is responsible for processing that template and creating and or updating or deleting resources. The CloudFormation engine inherently knows the order in which things should be built. It already knows that it should build the VPC first before it builds the subnet, before it launches the EC2 instance. It just knows a lot of those things. We don't have to worry about that order. But in cases where it gets ambiguous, such as launching a database in an EC2 instance, we do have control over the order. Once we upload a template to the CloudFormation engine, and the CloudFormation engine has created these resources, we can manage the collection of those resources under what we call the stack. That is the larger umbrella of all of those resources. So let's say that we have a very complex architecture with VPCs, subnets, EC2 instances, load balancers, and so on and so forth. If we reach a point where we don't need that infrastructure anymore, then we can just go in and delete the stack. And by deleting the stack, we then delete all of those resources. That's a whole lot easier than going in and manually picking through your environment and worrying whether or not you're deleting the right thing versus the wrong thing. So with CloudFormation, we have what we would consider declarative programming. Imperative programming is concerned with the exact order of things. You're saying, do this step, then do that, then do that. You're actually telling it what to do and how to do it. With declarative programming, we're just declaring the resources that we want, the ways in which we want those resources connected, and we allow the CloudFormation engine to worry about how those get built and in what order those get built. And again, these templates, because they're just JSON text files, they should be stored in source control. And I can speak from personal experience that having your CloudFormation templates under source control not only makes working with a team a whole lot easier, it makes rolling back to a previous version a whole lot easier. It makes it a predictable place to know where you can find that particular template. With CloudFormation, we can nest our templates. We can put one template inside of another one. And we can write that template once and then deploy it to numerous applications. Perhaps we have an architecture that we want to mirror across development, testing, staging, and production environments. And so we can write that template once and deploy it many times. Now, another nice thing about CloudFormation is that it does not impose any particular model for development and operations. It just gives us the absolute flexibility to create our architectures the way we see fit. Within a template, we will declare certain things such as parameters, or what we could also describe as variables. We'll describe the resources that we want to create, such as VPCs and EC2 and RDS instances. We can also create what we call mappings. These are another form of variable that help us map one value to another value. And then, of course, we can control the output of that template as well. So perhaps we want to create a load balancer, and then from that, once that's created, we want to get some of the attributes of that load balancer back as output. So let's take a look at an example template. Again, this is JSON, as you can see by the curly braces and the key value pairs that we see here. One parameter might be the CIDR range. So at the time we launched this particular template, any parameters that we have listed here, this right here, CIDR, would be the name of that parameter. When we upload this into the AWS console, we will be presented with a text field with this particular text, CIDR, off to the left as the label, and it will give us a place to type in a value, and that particular text box will be pre-populated with this value here, with the default. And so we would use this parameter. You'll notice here we're going to use this parameter later as a reference in our resources. Our resources, again, are the very things that we want CloudFormation to create for us. In this example, we're asking CloudFormation to create a VPC, and within its properties, we're going to say that the CIDR block of that VPC should be pulled or referenced to the CIDR parameter that we specified up here. So that gives us the ability to, instead of hard coding our IP range here, it allows this particular template to be flexible so that we can launch the same exact infrastructure, perhaps into multiple CIDR ranges. Perhaps we have a load-balanced application that needs to serve different applications, so each one gets their own CIDR range. So this is just a little bit of an example of the possibilities with CloudFormation. These templates can get incredibly complex, but it makes creating complex infrastructures so much easier by allowing one service to handle all of the details of the creation of these resources for you. So that is AWS CloudFormation. Now let's run through a demo of creating resources with AWS CloudFormation. Here we are back at the console. From here, from the dashboard, I'm going to click on CloudFormation. From here you can see we don't have any stacks yet. Before we get into creating a stack, I want to show you a template that I've created that will create a VPC, subnets, an internet gateway, and a few other things. So here's our template. Again, we have our parameters, which will specify some CIDR ranges for our VPC and for various subnets. And then you can see the rest of the template is dedicated to creating resources. We have route tables, network ACLs, we have ACL entries. A little bit farther down here, here's our VPC. You can see we're referencing the CIDR parameter. We're also going to tag this and reference the stack name that we give our stack. And you can see this template does get fairly involved. There's quite a bit going on here. There's quite a number of resources that are being created and managed by this template. I would recommend looking for tools. There are a number of tools out there that will help create these templates for you. One of them is, of course, the designer within CloudFormation. We can use the designer, which is just a rich UI and drag and drop tool set. There are other services out there, such as VisualOps, just to name one. And these tools can allow you to drag and drop different resources, and they will create the template for you. So a template as rich as this one and as complex can be challenging to start writing from scratch just because there's a lot of room for syntactical error. But as long as you're using an appropriate editor that can highlight errors like this, by causing a syntax error, we get a highlight there, then that does make it a lot easier. So from here, I'm going to just say create a new stack. I'm going to upload one. I'm going to choose my vpc.json. I'm going to click next. And of course, it'll ask us for a stack name. I'm going to call this one AWS Live Lessons VPC. And this one is going to create a VPC, and it's going to give us 3 private subnets and 3 public subnets. Typo there in my description, but that's okay. As long as my parameters are named correctly, that's really what matters in this particular case. So I'm going to choose, for this example, I'm going to choose 10.10.0016. And for my private subnets, I'm going to go with 10.0.0.24, comma 10.1.0.24, and 10.10.2.0.24. So those 3 ranges will be my private subnets. I'm going to copy those. This is just a comma delimited list. So my private subnets need to be 3 different ranges. So I left off at 2. So here I can do 10.10.3, 10.10.4, and 10.10.5. Just want to glance at that real quick and make sure I'm not missing any periods or slashes or whatnot. All right, I'm going to click next. And here I have the opportunity to tag my resources. So I might want to add like an environment tag, such as dev, stage, production, so on and so forth. I might want to add a name tag. Or maybe I want to call this one networking. Now, I do want to point out something under the Advanced tab. We do have the option to get notifications from this CloudFormation stack. If it were to fail or succeed, we could get those by leveraging the Amazon Simple Notification Service. Another important point here is the rollback on failure. This defaults to yes. So let's say that we get 90% of the way through. We've created 9 out of the 10 resources. And right there on the 10th resource, there is an error that prevents that resource from being created, and as a result prevents the entire stack from completing. Rollback on failure, if we have this checked as yes, that would essentially stop the stack creation and then go back and delete all of those 9 resources that were successful, and it would roll it back all the way to the beginning as if nothing ever happened. Sometimes you want that, but in other cases, by having it roll back on failure, if there was a problem and then it rolled back and deleted that resource, that could make it difficult to troubleshoot what the problem was. So a lot of times I will say, no, don't roll back on failure, just stop there, leave everything in place so that I have an opportunity to go in and do some troubleshooting. So from there, we'll click Next. Just to review this real quick, we have our stack name, we have the CIDR range of our VPC, we have our 6 private subnet ranges, and I'm going to go ahead and hit Create. You can see our stack is now actually creating. On the Events tab, we can see things coming in pretty much real time as different resources are being created. You can see I've got an internet gateway, a VPC being initialized. There we go, our gateway and our VPC are both complete. Some subnets and route tables and security groups that still need to be created, so we're still waiting on those. I'm going to hit refresh. You can see that. Here are all of our network ACL entries, our routes. A few other things have completed. While that's going, I can show you a few other things like the template itself. We can see the template that's being used. We can see the parameters that we entered. We can see the tags that we applied. We can also go back here and see the resources. These are all of the various resources that are being managed under the umbrella of this particular stack. And like I mentioned before, all of these things, if we were to do this manually, look at all these resources, it would take time. It would take a lot of time, even just to do it once, let alone to do it multiple times across multiple environments or multiple regions. And then, of course, we have the human error factor. So you can see that even just with a simple template like this, that the CloudFormation service makes managing all of these resources a whole lot easier. At some point, if we decide that we no longer need these resources, we can just simply highlight this stack, go up here and say delete, and then it will handle the deletion of all of those resources for us. And there we go. Our stack has gone into the create complete status. We can see here that all of our resources have completed their creation. We can see here are all of our resources. And now, of course, if I were to go back to, let's go back to VPC, and I'll show you that here we are. We have the new VPC that was just created, the 1010 range, and you can see that we have 3 private and 3 public subnets. We have some route tables. We have an internet gateway. We also have some network ACLs for public traffic and for backend private traffic, along with corresponding network ACL entries. So again, these were a lot of individual resources that were created very quickly and very easily by leveraging the CloudFormation service. So just to go back real quick and review that, all we did was, we created a stack, we uploaded our template, added a few parameters, and allowed the CloudFormation engine to build the resources that were specified in this template. So that is creating resources with AWS CloudFormation. Now let's review some application management services. The first service here that we want to talk about is AWS Elastic Beanstalk. Now we talked about earlier CloudFormation. If you think of these services on a scale of absolute control on one hand and absolute convenience on another, CloudFormation would be near the far end of control, and Elastic Beanstalk would be on the very far end of convenience. So we get a lot of convenience with Elastic Beanstalk, but certainly nowhere near the amount of control that we get with AWS CloudFormation. So Elastic Beanstalk is what we would consider an application management platform. It provides very easy entry into Amazon Web Services. There's a couple of ways that we could think about Elastic Beanstalk. One way is that it's ideal for developers. There are plenty of folks out there that all they want to do is write their application and see it run. They don't want to bother with managing servers or resources. They don't want to install Nginx or Apache or PHP. They just want to write their application and hand it off and allow some other service to manage the underlying infrastructure for them. So in that case, developers simply upload their application. They can choose from a number of different platforms like Java, .NET, Node.js, Docker, among others. And by uploading their application to the Elastic Beanstalk service, the Beanstalk service will handle the creation of resources and the ongoing management of those resources automatically. So when we upload our application, we can choose to have it load balanced, in which case Elastic Beanstalk will create the ELB and manage that for us. If we want our application to be auto-scaled, which we'll talk more about later, we can choose that as well. Elastic Beanstalk handles capacity provisioning and monitoring all automatically in the background for us. There's really no degree of infrastructure management that we have to worry about. So another way to think about AWS Elastic Beanstalk is for IT teams that just have a lot to do, and we don't necessarily have time to design, deploy, and manage these resources independently. Perhaps we have more important things to do with other systems, and we just want to take a particular application that was handed to us and use Elastic Beanstalk as a way to save time. Just get it into Amazon and trust that the Elastic Beanstalk service will keep that application highly available and fault tolerant. The next service that I want to talk about is AWS OpsWorks. So again, if we go back to that scale of convenience versus control, where on the very far side of convenience we have Elastic Beanstalk, and on the very far side of control we have custom scripts that we write. Somewhere in the middle, giving us a little more convenience but still absolute control is CloudFormation. And then giving us more convenience but slightly less control is AWS OpsWorks. Now, OpsWorks is somewhat similar to Beanstalk in that it is an application or what we might call a configuration management platform. It's still going to give us a high degree of convenience, but a whole lot more control than we get with Elastic Beanstalk. Now, when we talked about AWS CloudFormation, one point that I made there was that CloudFormation does not impose any specific model of deployment or operations. It's wide open. We can do what we want. But OpsWorks does have a model. It's based on these ideas of stacks, layers, and applications. These are based on Chef recipes. So for those of us that might be familiar with Chef, we have access to running Chef recipes, which we might call configuration as code. We're going to get more control than Elastic Beanstalk, but we're going to get a narrower range of resources than we would have access to with AWS CloudFormation. But we still get to say that within our stacks, we're going to have control over all of the infrastructure that is being managed, the infrastructure and the applications that are being managed. Within a stack, we have layers. So each layer represents the particular types of instances and related resources. So one architecture might be classic three-tier architecture, where you have load balancers out front, you have application servers, and then in the back you have database servers. So perhaps each one of those is its own layer, where one layer describes your load balancer, another layer describes the particular types of instances you want being used for your application, and then yet a third layer is describing the types of database resources that you want. And again, all of those layers together would be represented by one stack. And then of course we have our applications. So in that example, that second layer, we would deploy an application to that layer or to the instances in that layer by leveraging chef recipes that can control exactly how and when our application gets deployed. And then, of course, once we deploy our applications into these layers and into these stacks, the OpsWorks service will continue to maintain our application health by replacing instances that fail. It can also help us to automate the management around scaling and capacity provisioning as well. So OpsWorks is ideal for IT admins, DevOps engineers, those who want convenience in their infrastructures, but want more control than what we get with AWS Elastic Beanstalk. So those are our application management services. Here we'll run through a demo of launching an application on AWS Elastic Beanstalk. Again, from what should be by now the familiar AWS console, under the compute category, I'm just going to go over here to Elastic Beanstalk. And again, as I've mentioned, Elastic Beanstalk really lowers the barrier to entry into Amazon Web Services. There are plenty of developers out there who either don't have time or the inclination to bother with the underlying infrastructure. They just want to write code, they just want to ship code and allow something else or someone else to deal with infrastructure. And so Amazon Elastic Beanstalk is the answer to that. So here, it's really easy to get started. In fact, for those of us who are coding with Java using Eclipse or .NET using Microsoft Visual Studio, there are plugins into those IDEs that make it really easy to get your application into Elastic Beanstalk directly from your IDE without ever having to log into the AWS console. You can just stay right there within your IDE and deploy versions of your code directly into Elastic Beanstalk. So for the sake of this demo, we're just going to choose one of these pre-configured platforms. I've been a fan of both Go and Node.js for a number of years now, and a lot of the places that I have worked or clients that I've worked with leverage Node.js very heavily. So that's what I'm familiar with, so we're going to go ahead and choose that. You can see here that by choosing that, we're going to create an environment running Node.js on 64-bit Amazon Linux. So I'll go ahead and launch that. There we go. Elastic Beanstalk is launching our environment. Now, behind the scenes, Elastic Beanstalk does actually make use of AWS CloudFormation, but it sort of wraps a convenience wrapper around that. It gives us much more convenience and, like I said, a lower barrier to entry. We can view the events as it's launching our environment. There we go. Created the load balancer. We can always refresh this if we think it's going a little slow. Here's our configuration settings. So you can see while it's building, we'll review this. We can adjust scaling. We can say, yes, this environment type should be load balanced and auto-scaled. We don't really need to know what it takes to achieve that as long as we're using Elastic Beanstalk. All we need to do is come in here and click the gear and say, yeah, that's what I want. I want it to be load balanced and auto-scaled and allow the service to handle the creation of those resources. With auto-scaling, we could say, you know what, I want a minimum of 1, maybe a maximum of 4, maybe a maximum of 40, whatever it is that we're willing to pay for. It doesn't really matter what availability zones are used. Perhaps I want to use all 3. We can define scaling triggers. On this one, it appears that we have scaling triggers set to measure the network out, or the amount of network traffic that's going out. We're going to average that over 5 minutes. And then when it's above a certain threshold, what is that, about 6 megs, then we can trigger a scaling event. We can adjust the type of instances that we want. T2 micro looks to be the default, but we could change that if we wanted to. Perhaps we would prefer something like an M4 large. And of course, we can't really save this while our environment is currently building. We'll have to wait until that is complete before we can make any of these changes. But you can see that the service makes all of these different settings that would normally be found in various different places. It brings them all together under one UI, and it makes it really easy to configure an application and the underlying infrastructure. You can see here we're using Node version 6.9.1, which happens to be the latest at the time of this video, and we're still waiting on that application to become healthy. And there we go. It looks like it's up. So we can go back to the dashboard here. You can see that our application is running. It says that the health is okay, and the recent event says that we've added some EC2 instances, we've launched our environment, and everything is up and running. Now, from here, here's the URL for that particular load balancer. If I were to click that, we should get, there we go, we get the default page for that application. And this particular web page came from a Node.js application running on an EC2 instance behind a load balancer. So if we wanted to upload our own application, then all we would have to do is package it appropriately and then upload and deploy. So again, Elastic Beanstalk makes it really easy for just about anyone to get their application into Amazon Web Services very quickly and very easily, and that is launching an application on Elastic Beanstalk. If you've been in IT or software development long enough, you'll probably recognize some fundamental building blocks that many applications leverage, such as message queuing, sending emails, monitoring, and notifications. In this lesson, we'll explore these tools offered by Amazon Web Services, along with other exciting technologies that ease the development of mobile applications. Now let's talk about Amazon Simple Queue Service. Amazon Simple Queue Service, very much like other Amazon services, is built to be inherently highly available and fault tolerant. So with a queue service, we can put messages in, buffer those messages up for some period of time, and then pull them back out. The Simple Queue Service, or queues in general, are a really great way to introduce loose coupling into our applications. So loose coupling, or that is the ability to separate different applications so that they can scale independently, they don't have any inherent knowledge of each other. That's a really great practice in order to be able to scale out and handle large amounts of traffic and large amounts of data. So with the Simple Queue Service, we can handle millions, even billions of messages without having to worry about the underlying infrastructure of that service. Amazon just handles it for us. Now, the messages that we put in here will be stored redundantly across multiple servers and multiple availability zones, very much like Simple Storage Service in DynamoDB. With the Simple Queue Service, messages will be pushed in and then pulled out. We actually have to go in and ask for the messages. They're not published like with other services. We actually have to ask for those messages by way of polling. It's important to understand that with the Simple Queue Service, the message order is not guaranteed, but we do get a guarantee of at least once delivery. Now that means that a message could be delivered 2 or 3 times, but it will be delivered at least once. We can leverage resource-based policies and IAM policies to control who is allowed to use this particular queue, even sharing it with other accounts. We can also allow this queue to be written to and read from anonymously if we wanted to. Another important feature of the simple queue service is what we call the visibility timeout. Now, the way that this works is that, let's say that we have an application down here on EC2 that's pulling messages out of the queue. And we've pulled message A out of the queue, and whatever that message is, perhaps that message is a notification about a video that is ready to be processed, or some other type of data that needs something to be done to it in the background, asynchronously. So we pull message A out of the queue, and once we acknowledge receipt of that message, the queue will now mark that message A across all of the partitions is now considered invisible, or it's locked, so that no other system, if we have our application distributed among multiple EC2 instances, we don't want that message to be processed twice. So now, once we've retrieved it by one, it's now invisible to others. The default visibility timeout is 30 seconds. We can change that if we wanted to, and that gives us time to process that message. If processing fails and the message is not deleted within that timeout window, then the message will become visible again so that it can be picked up by another EC2 instance, and then processing can resume. So this is a really great way to prevent multiple components from processing the same message at the same time. But again, we do need to keep in mind that because of that at least once delivery, it does mean that if, let's just say that this machine deletes the message, and then 10 milliseconds later, another EC2 instance polls messages, it's still possible that this EC2 instance will still get a copy of that same message. And so our application needs to be what we would call idempotent, meaning that if we were to process the message twice in a row, we're still going to get the same result. Another approach to that would be to record the fact somewhere, perhaps in DynamoDB, we might record the fact that we've already processed this message so that we don't have to do it twice. So that is Amazon Simple Queue Service, a really powerful service for buffering events, buffering messages, to enable loose coupling and asynchronous processing between layers of our application. Now let's talk about Amazon Simple Notification Service, otherwise known as SNS. With Amazon Simple Notification Service, we have a slightly different model than what we saw with the queue service. With the queue service, it was based on putting and pulling, or polling and actually asking for messages where they were buffered within the service. Here, it's more of a publish-subscribe method, where what we do is we create what we call topics within the Simple Notification Service. And then when we publish messages to those topics, those messages get delivered by way of either email. We can deliver those messages to a HTTP or HTTPS endpoint. We could deliver them through mobile text message, through mobile push notification, or we could have those messages pushed into a queue under the Amazon Simple Queue Service. These would be what we call our subscriptions. We would subscribe to these topics through these various methods. And again, when messages are published into those topics, those messages or notifications are then delivered to those subscribers via whatever methods they had subscribed to. So perhaps our video status topic, we want to subscribe via a JSON email and a text message. And our order status topic, perhaps we want to subscribe via HTTPS, and we could subscribe a simple queue service queue to that so that we can leverage some other system to pull from that queue and allow them to buffer up and pull asynchronously. Now, with the Simple Notification Service, it's important to know that the order is not guaranteed, very much like the Simple Queue Service. and messages are not stored. As soon as a message goes into a topic, and then once it's delivered out to its subscription endpoints, it is no longer stored. And it's also important to understand that we do have a 64K message limit. So the Amazon Simple Notification Service is a really great way to get messages out. Perhaps you want to get messages out to some kind of an email system. You want to get a message into something like PagerDuty. You want to be notified of a CloudWatch alarm. You want to be notified of something going on within your application. So that is the Amazon Simple Notification Service. Now let's talk about Amazon Cognito. Amazon Cognito is a fairly rich service in itself in that it does a number of really useful things, especially in regards to mobile applications. So one of the great things that Amazon Cognito does is help us with identity. By integrating with major authentication providers like Twitter, Facebook, Google, so on and so forth, a number of others, it allows us to implement single sign-on or log in with Facebook, log in with Twitter on any device or any platform. It could be laptop, desktop, tablets, mobile devices. Instead of writing all of the various code to account for all of the differences between these various providers, because they all do things slightly differently, Twitter versus Facebook versus Google, we simply write against one platform, that is Cognito. We write against that one service and allow that one service to handle the details of these various services for us. It also helps us manage unique identities across various platforms and devices and helps implement temporary keys, as we've talked about before. So in the cases where we have mobile applications that need access to other Amazon services, we can leverage that single sign-on, log in with Facebook, log in with Twitter, and then leveraging Cognito and the security token service, we can implement temporary keys and deliver those temporary credentials back to our mobile application, and then allow our mobile application to call other AWS services directly, such as Amazon Simple Storage Service, Amazon DynamoDB, and so on. Another really powerful feature of Amazon Cognito is Amazon Cognito Sync. And this is a tool that allows us to sync data between various applications and platforms. So let's say we have different app data and we have that application on a desktop, we have it on our tablet, we have it on our smartphone, and Cognito can help sync that data between these different devices. Perhaps we want to save the state of our game or the state of the book we're reading. Perhaps we want to maintain the same preferences from device to device. It works across various devices. It works across different operating systems. It can also enable us to allow our users to work offline by storing data locally in a SQLite database. And so whether or not the user is online or not, they can continue to work storing their data locally. And then once they're back online, then Amazon SDK can automatically resync back to the Cognito service. So you can see Amazon Cognito is a really powerful service that enables a lot of the hard work and the drudgery of developing for mobile applications. Single sign-on, syncing, these are common things that most applications need to do. So why reinvent the wheel? Why bother with all of the details of logging in with various services and syncing between various platforms? Just leverage one service that helps you do all of that, and that is Amazon Cognito. Now let's talk about Amazon Mobile Analytics. With Amazon Mobile Analytics, this service makes it really easy to measure the usage of our applications. So we have mobile applications out there, and we want to understand what our users are doing. What are the trends that are going on within these applications at any particular period of time? What's the retention of our users? Are they coming back? And if they're coming back, what are they doing? What are their behaviors? And by understanding these things, we can start to understand how to make our app better. We can start to understand ways that we can further monetize our application as well. And instead of writing a service to do the analytics for you, perhaps you want to just leverage an existing service such as Amazon Mobile Analytics. So it's very easy to get started simply integrating the AWS Mobile SDK, which supports iOS, Android, Fire OS, and Unity out of the box. Otherwise, we could leverage the REST API directly. And then once we start sending information into the mobile analytics service, we can see reports within 60 minutes. And then, of course, another important point is that you own the data. Some of those other analytic services out there, if you read the fine print, they will say that they own the data, and then as a result, they're allowed to sell it to other people. But with Amazon Mobile Analytics, you own the data and you can do with it what you want. Now, technically speaking, the mobile analytics service collects 3 types of events. We have system events such as the app started, the app shut down, things like that. We have in-app purchases as an event, and then we have custom events that we get to define depending on the nature of our application. So again, Amazon Mobile Analytics is a service that makes it really easy to implement analytics into our mobile applications. Besides security, perhaps the most important requirement of any infrastructure is uptime. After all, what good is an application that isn't running or can't scale to meet demand? In this lesson, we'll explore Amazon Elastic Load Balancing, autoscaling, and discuss concepts pertinent to achieving a superior degree of high availability and fault tolerance. Let's talk about elastic load balancing. Elastic load balancing is a really powerful feature within Amazon Web Services that can help us enable a highly available and fault-tolerant application. Now, the elastic load balancer, by creating one, it is inherently highly available and fault-tolerant. As we'll talk about later, it is comprised of multiple nodes, and so it has that fault tolerance built in to it. It's also self-healing, and we don't have to worry about any of that. When we create an elastic load balancer, we're trusting that that elastic load balancing service will handle itself, it will heal itself and scale itself. Now, when we create one, at the time we create it, we will specify which subnets we want that load balancer to exist in. In this example, our elastic load balancer has a network footprint into 2 different subnets so that we can span multiple availability zones. We also have multiple EC2 instances behind our load balancer, also in leveraging multiple availability zones, so that now we can say, going back to our very fundamental architectural question, what happens when this component fails? We could say, if this component fails, we have another EC2 instance that can continue to handle traffic. What happens when an availability zone fails? Well, we still have another availability zone. We can still continue to handle traffic. So it's a good idea when we create an elastic load balancer and we create an application on EC2 that we use every AZ within that region. When we create an elastic load balancer, the way that we connect to that is by way of a DNS endpoint. Now, some of the magic behind the scenes that we'll talk about later means that we can't rely on the IP address of that DNS endpoint because they change. They are subject to change at any time. And I've seen this happen. This actually happened to me in the very early days of my own Amazon experience. I did exactly what the documentation says not to do. I took the IP address, I did a host lookup, took the IP address from the DNS endpoint and added that as the A record for my domain root. And sure enough, the IP address changed. The original IP address that I had taken was given to someone else, and the next thing I knew, I was seeing someone else's website on my domain. So that's not what we want to happen. So don't rely on the IP address that you're given. Don't try to use that in any kind of long-running DNS kind of situation like I just mentioned. Continue to connect to the DNS endpoint. That way the IP addresses can change as nodes come and go underneath the Elastic Load Balancer. Throughout this course, we've talked a little bit about, you'll pay this here and you'll pay that there. Typically, I don't try to remember the dollar amounts that we pay. The billing model within Amazon Web Services is just too rich for me to remember everything. What I try to remember is what I actually pay for, not necessarily how much I pay, but what I pay for. So in the case of the Elastic Load Balancer, we will pay a certain amount per hour plus a certain amount per gigabyte of bandwidth. The Elastic Load Balancer comes in two different flavors, or what we call a scheme. And we can either choose an internet-facing load balancer or an internal load balancer. They're functionally identical. They do the same thing in the same way. The only difference is that the internet-facing, as you probably can guess, will get a public IP address, and of course that's good to use for publicly available services, APIs, and websites. But for internal use, in the case of like a 4-tier system where you want to separate your web tier or perhaps a proxy or a caching tier apart from your application layer, then an internal load balancer is a good thing to use there. So the internal load balancer simply gives you a private IP address. And that's really the only difference. So the Elastic Load Balancer is one of the most important and powerful keys to creating a highly available and fault-tolerant application within Amazon Web Services. Here we'll discuss listeners and SSL certificates for the Elastic Load Balancer. In order for an Elastic Load Balancer to receive traffic, we have to add what's called a listener. Now, we could say that we might want to listen for HTTP traffic on port 80. We might want to listen for HTTPS on 443. We could also listen for just raw TCP traffic as well. Now, if we're wanting to accept HTTPS or SSL traffic, we need to specify an SSL certificate. The load balancer does support SSL offloading so that we can remove the burden of encryption from our back-end machines. And in doing so, what we would do is we could use the command line tools to upload our server certificates to the IAM service. Right now, it's not possible to do this within the AWS console. We would have to use the CLI tools to do that. And then once we create that HTTPS listener, we would choose one of those certificates. We could also, as an alternative to uploading a certificate to IAM, we could use the Amazon Certificate Manager to create a certificate for us. In that case, certificates, including wildcard certificates, are completely free. They're trusted among major browsers, but they're only for use. You can't really get that certificate out. You can only use it within Amazon Web Services. But still, it's a really great way to get a free certificate using the Amazon Certificate Manager. So either way, whether you upload one to IAM or use an Amazon Certificate Manager, we would choose one of those for the HTTPS listener. Now, when we specify a listener to listen on port 80, we also need to specify to what port we are forwarding that on the back end. You can only have one listener per front-end port. So on port 80 coming in, we can only have one. but we can have both of these listeners forward to port 8080 on the back end. So this is an example where we don't have SSL back here on our EC2 instances. We're just listening on port 8080, and we're going to forward both of these connections, both unencrypted and encrypted connections, to the same port on the back end. Now, if you wanted to get the IP address that the initial request came from, the client IP address, you'll need to look to the X forwarded for header. That will specify the IP address that a request came from. So again, in order for a load balancer to receive traffic, we need to create listeners of some kind, whether it be HTTP, HTTPS, or TCP, and then choose some kind of a port to forward those to. And in the case of HTTPS, we need to choose an SSL certificate. So those are listeners and SSL certificates for the Elastic Load Balancer. Now let's talk about load balancing algorithms for the Elastic Load Balancer. Under the hood, behind the scenes of the Elastic Load Balancer, the way that this works is that it creates what we call nodes. And of course, this is not something that we really have to worry about. It's just interesting technical knowledge so that you can understand the behavior of the Elastic Load Balancer. So we have nodes. You'll notice here that the Elastic Load Balancing service will place a node in every subnet that we say we want to use. And again, it's a good practice to use every availability zone in that particular region. So we have these multiple nodes. Each one of them will get its own IP address. If you're using an internet-facing ELB, these nodes will get public IP addresses. If you're using internal Elastic Load Balancer, then these nodes will get a private IP address. Now, as requests come in from either the internet or they come in from a private service, wherever they come in from, once they reach the load balancer, they are distributed between these two nodes via DNS round robin. So it's just going essentially back and forth between these nodes. Now, as your traffic grows and as you start to receive more and more requests, the Elastic Load Balancer will automatically scale the number of nodes to handle that incoming traffic. Now, there are times when traffic is spiking faster than the Elastic Load Balancer is scaling. And some people seem to find that the Elastic Load Balancer doesn't scale fast enough for their particular traffic patterns. So in those cases where you do expect traffic to spike, you can submit a ticket to Amazon support and ask them to, quote unquote, pre-warm your Elastic Load Balancer and go ahead and initiate that scaling event ahead of that wave of traffic, and that will get you more nodes here under the hood. So again, as traffic is coming in, it is being distributed among these nodes via DNS round robin. Between the node and the backend instances, we're going to use the least outstanding requests as a way to determine which backend node should handle that particular request. You can see here, again, we're leveraging multiple availability zones. As our traffic begins to scale, we would see that we would start to add, probably through the auto-scaling service that we'll talk about here coming up, but we would start to add multiple EC2 instances, maintaining a balance across these multiple availability zones. Now you'll notice here that we have multiple instances across multiple availability zones. In this case, we're using US West 2. So in this example, we have 2A and 2C. It's possible for a load balancer node over here in 2A to send a request off to a backend instance in another availability zone, and we call that cross-zone load balancing. That is an option that's enabled by default. We can turn that off if we want to, but it's important to know that it can help maintain an even balance of requests across our servers, but it does incur an additional cost. The data being transferred across availability zones will cost us an additional bandwidth charge. So again, requests coming in initially are balanced between nodes of the load balancer via DNS round robin. Between the load balancer node and the backend service, those are handled via least outstanding requests. Now let's run through another demo of creating an elastic load balancer. Again, from the AWS console dashboard, I'm going to go to EC2. That's where we find the elastic load balancer. I'm going to scroll down here to the bottom. You can see load balancing. Under load balancers, we have one that was created from an earlier demo, an earlier exercise, so I'm going to just leave that one as it is, and we're going to hit create load balancer. From here we have two choices. We could create an application load balancer, which actually does layer 7 load balancing, looking at the content, or we could choose a classic load balancer, which is just a lower layer at the port layer. So we're going to choose classic load balancer, just as an example. Click continue. I'm going to call this one again AWS Live Lessons. I'm going to choose the VPC. In this case, I'm going to go with the one that we've created in an earlier demo. Here, actually, on second thought, I want to go with one that actually has some instances running in it. We need at least one listener. Again, I could choose HTTP, HTTPS, or just raw TCP. For this demo, I'm just going to choose HTTP and add that listener. In order for our elastic load balancer to have a network footprint into our VPC, we have to choose some subnets. And so it happens that this particular VPC only has 2 and both of them are public, so I'm just going to go ahead and add both of those. Next, we can assign security groups. Whoops, I ended up inadvertently adding an extra listener, which we don't need, so I'm going to remove that one. We're going to assign security groups. You can see here we have a security group for our web servers, but typically it's a good practice to have a security group per function or per tier. So our load balancer would typically get its own security group. So I'm going to go ahead and say create a new security group. I'm going to call this one AWS Live Lessons ELB. And I'm going to say I want to allow HTTP traffic from anywhere. Going to configure a health check. And from here, the health check is how the load balancer knows that our backend instances are indeed healthy and sending the proper response. So it's up to us to configure this appropriately. So yes, I'm going to assume that my server is listening on port 80 and my ping path will be whatever that application is set to. Sometimes it could be just /, it might be status. You could configure your web server with a very specific health check path. So long as your backend server returns an HTTP 200 response, then the ELB will consider it healthy. Anything other than a 200, any 300 responses, 400s and 500s will be considered unhealthy. In the case of using the elastic load balancer along with auto-scaling, if the ELB determines that your instance is unhealthy because it's gotten too many non-200 responses, then the ELB will report an unhealthy status to the auto-scaling group, which could mean that your instance will be terminated. Sometimes you want that to happen Other times you might not. So really take your time to understand what the health check should be for your particular application. Here, we're going to give that health check 5 seconds to deliver a response, which actually is a really long time. We're going to do it every 30 seconds. We could change that to 60 if we wanted to. We're going to say that it's going to take 3 checks in a row, returning non-200 responses to set that particular instance to be unhealthy. I'm going to change this one to 2 and say that it takes 200 responses in a row in order for the machine to be considered healthy. Next, we can add EC2 instances. You can see that we have our choice of these 2 that are running within the same VPC, within the subnets that we've chosen. I'm going to go ahead and add these, even though I know we don't necessarily have these configured yet for HTTP traffic, but we could come back and do that later. You can see here that cross-zone load balancing is enabled by default, and connection draining is also enabled by default. Connection draining says that here we have it configured for 300 seconds, which is also a very long time. It's 5 minutes. And connection draining just says that if we are going to remove an instance, whether we do it manually or we allow autoscaling to do it, if we're going to remove an instance from the load balancer, before the load balancer lets us do that, it's going to stop receiving incoming connections, and it's going to allow the outstanding request to finish. That's important because if we just simply yank an instance out from behind the load balancer, users could end up with a blank white page. They could end up with half a file downloaded, and we don't want that. So connection draining allows those in-flight requests to be finished. Though I usually lower this to something more reasonable. I generally think 300 seconds is a long time, especially for APIs. Most requests should happen in a mere fraction of that. So we could lower that to whatever makes the most sense for our application. We're going to add some tags. Again, I typically like to add, this is my particular pattern. I have my own way of organizing an infrastructure. But again, you should be leveraging tags to organize it in whatever way makes the most sense for your business. Ultimately, I think the most important thing, regardless of the names of the tags you use and the values that you use, I think the most important thing is that you find a pattern and stick to that pattern so that you can predict what the tags will be and be consistent about it. So here, again, AWS Live Lessons, ELB, and I'm going to add an environment variable. And now we can review this, make sure that we have everything set the way we think it should be. We're in the right subnets. We have the right instances in place, and I'm going to go ahead and hit create. There we go. Just like that, our load balancer is created, and here it is. This is the one we've just created. We can scroll down here and see that it is an internet-facing load balancer. Here's our DNS name. So this is how we would connect to that. We would point our end users to this DNS entry. More likely, we would use this DNS entry as the destination of a CNAME, or within Amazon Route 53 DNS, we could create what we would call an alias record out of this. Here's our instances. You can see that these 2 instances were registered with the load balancer, and you can see they are out of service because they're still registering with the load balancer. It sometimes takes it a minute for the services to fully register with the load balancer, and then it'll take even more time, perhaps another minute, for it to pass 2 consecutive health checks. We can go over here and review our health check and make changes to that if we want. We can see the listeners that we've put in place. We can edit that and add a HTTPS listener. And of course, in order to do that, we would have to have an SSL certificate, which we don't have. But we could get one for free through the AWS Certificate Manager if we wanted to. So I'm going to cancel that and just leave it at HTTP for now. We can also see monitoring. This is out-of-the-box monitoring. So once we start getting traffic, coming through this load balancer, we could start to see, one being the number of unhealthy hosts versus healthy hosts. We can see latency, the number of requests that we're getting, back-end connection errors, 500s versus 400s versus 200s, and so on. So again, once we have traffic, we'll start to see some graphs here. So that's it. That's really easy to create an elastic load balancer. Here we'll talk about autoscaling. The autoscaling service is an incredibly powerful service that allows us to handle changes in traffic or changes in the demands of our application. Now, one of the really key features of not only Amazon Web Services, but cloud computing as a whole, is the ability to be elastic. We're operating from a paradigm of use what you need and pay for what you use. So if we don't need it, why should we be paying for it? If we don't need, massive servers, we should be paying for smaller ones. If we don't need 1,000 machines, we should be paying for fewer ones. We want to be looking at our traffic, looking at the demands of our application, and really saying, what's the minimum that we need to fulfill these requests and meet this demand? And then as that demand rises, again, we ask that question, okay, from this point on, what's the minimum that we need? And we keep doing that as demand rises. And then, of course, as demand falls, we want to be reevaluating that and going, you know what, demand is coming down. We don't need this amount of compute power, so let's pull these machines out and save money. So the autoscaling service can help us with that. We have our VPC, leveraging multiple availability zones. We have an elastic load balancer, leveraging multiple availability zones, as is our application in multiple EC2 instances across multiple availability zones. What we have here is an autoscaling group that is designed to launch machines into multiple availability zones. As our traffic increases and we start to see perhaps that we're going over some threshold, maybe it's CPU or network or the number of processes, then we can allow the autoscaling service to start to add machines for us. And perhaps we want to start at 3 and go up from there. And so after a certain period of time, we see that our metrics have not lowered. We're still above a certain amount of CPU usage, we're still above a certain amount of network usage, whatever it is, whatever we determine the bottleneck to be, then the autoscaling service will continue to add machines for us and will continue to scale. Now, we do have some limits. We can set a minimum, we can set a maximum. Typically, the minimum would be set based on, how many machines do we need to maintain the minimum load or the lowest amount of traffic that we ever see. The maximum would be determined simply by how much we're willing to spend. Within Amazon, while we do have some initial limits on the number of instances we launch, we can very easily get those limits lifted. And perhaps we aren't willing to pay for 100 machines running. Perhaps we're only willing to spend money on 12 or 20, and so we can set that as our maximum. And now we can see that our system has scaled out and it's maintained a balance of machines across multiple availability zones. If we were to lose one of these machines, then autoscaling would automatically replace it. If we were to lose one of these availability zones, the autoscaling group is smart enough to know if that availability zone is unreachable, then it will automatically rebalance and put these 2 machines over here in the other 2 availability zones that are still in operation. Now, as our traffic starts to come down and starts to fall off, we can allow the autoscaling service to start terminating machines. So our traffic comes down even further, and we've removed 3 machines, we're back to our original minimum. So Autoscaling service can help us scale out to meet demand, and then during times where we don't have that demand, it helps us scale in to save money. And the scaling in is just as important, because one of the primary reasons so many people, so many Fortune 500s and government agencies are moving to Amazon Web Services is the opportunity to save money. And so it doesn't really do us any good to scale out to dozens of machines and just leave them there. We want to be sure that we configure our autoscaling group to scale in as a way to lower our costs. Now, in order to create an autoscaling group, two things are required. We're going to have what we call the autoscaling group itself, and then a launch configuration. Some things that are optional would be scheduled actions and scaling policies, and we'll talk about the details of these things here coming up. The autoscaling service can replace failed instances. It can change the capacity or the number of instances in that group. We could, in some cases, maybe we don't need to scale out and in. Maybe we just want to maintain 2 instances or 3 or 4 instances, some fixed number of instances. And so if one of them fails, autoscaling will replace it and just maintain that certain number of machines. We're going to see here in a little bit how autoscaling can work with Amazon CloudWatch so that we can leverage alarms to trigger scaling events. As our machines come and go, as machines are launched, as machines are terminated, we can capture those events with the Amazon Simple Notification Service as well as Lambda and do some kind of processing or coordination on that event. So let's take a look at the 2 things that are required: the launch configuration and the autoscaling group. The launch configuration defines what gets launched, such as the instance type. Maybe we want to launch a T2 small or an M4 large or a C4 extra large. So we define the type of instance that we're going to launch. We can specify the EBS volumes or the instance store volumes. We can specify the Amazon machine image, any user data that we want to use to bootstrap that machine. And once we create the launch configuration, it cannot be edited. We have to delete and recreate a launch configuration if we need to make a change to it. The other component that's required is the autoscaling group itself. Where the launch configuration determines what gets launched, the autoscaling group determines where it gets launched. And that is, here we specify what subnets, and by way of subnets, we thus specify what availability zones are being used. We also specify which elastic load balancers are going to be used. And yes, we can specify multiple elastic load balancers for an autoscaling group to use so that when instances are launched, the autoscaling group will automatically register those instances to the ELBs that we've defined. Within the autoscaling group, we also specify the health check type. Now, an autoscaling group needs some way of knowing whether or not a machine is healthy or unhealthy. If a machine is considered to be unhealthy, then the autoscaling group will terminate it and replace it with a new machine. We can get those health checks from either EC2 system health checks, or we can get the health checks from the ELB itself, and we can configure a health check on the ELB. If we specify tags, as we should be doing in order to keep our environments organized, we have the option of adding these tags to the autoscaling group, and then the autoscaling group can propagate those tags to the instances that are launched. A couple of things that are optional within autoscaling would be things like scheduled actions. So let's say that you're planning some large marketing event. Perhaps your business is going to be featured on the news, or perhaps you're launching some kind of campaign and you know that you expect a certain amount of traffic or a spike in traffic as a result. If you know about it ahead of time, we can schedule perhaps a one-time event, or I've worked with plenty of customers who have, if you look at their traffic patterns, it's like a regular sine wave. Every day at a certain period of time, they see the same spike, and every day at another time, they see the same trough. And so when you know you have those types of rises and falls in traffic, then we can leverage intervals to schedule, all right, every day at 4 o'clock, we're going to scale out, and every day at 8 o'clock, we're going to scale back in. And that's really helpful when you know the events ahead of time. Then you can get out ahead of that curve and go ahead and have those machines available before that traffic starts coming in. The other thing that we could do is what's called a scaling policy, and this allows us to scale based on a dynamic load. It's really useful for those times when you can't predict when that load is going to come in. Maybe just out of the blue, your website is featured on CNN, or out of the blue it's on the front page of Reddit, and all of a sudden you have 1 million more users today than you did yesterday, and you didn't expect them. And so we can leverage these scaling policies to scale our system in a number of different ways. Now, a scaling policy has to be triggered by something. We could trigger it via a CloudWatch alarm. We could trigger it manually, which is what we might call the push button approach. You just go into the console and say trigger and allow the scaling policy to do what it does. We could do it programmatically, perhaps even from within our own application. Maybe the application is smart enough to know that it's time to scale, and it can trigger the scaling policy. So leveraging the elastic load balancer, leveraging auto-scaling, leveraging our launch configurations, we can achieve what we call self-healing services. I don't know about you, but I personally don't really like being woken up at 2 o'clock in the morning to go in and reinstall and reconfigure Apache because our server failed. I don't want to have to do that. Our customers don't want to wait for us to do that. Our business owners don't want to be losing money because we were down for an hour or more. We want a system that can heal itself in the case of a fault. So if one of these instances were to fail for whatever reason, then we want the auto-scaling service to be able to replace it. We can leverage user data, as we've talked about, either adding environment variables or adding a script that installs what needs to be installed, configures what needs to be configured, and gets that machine bootstrapped and running as quickly as possible. So here's an example where perhaps we have a front-end web server tier that needs a little more CPU than it does memory. So perhaps in this tier, we have a launch configuration that uses a C4 large. And the user data just has environment variables and then starts the process. And the process looks to those environment variables to determine what environment it's in, what backend service to connect to, and so on. In our private backend service behind the internal load balancer, we also have an auto-scaling group that is with a launch configuration that leverages a different AMI. Perhaps this is an application AMI that already has our application installed and configured, but this one will use the M4 large rather than a smaller server because perhaps our application needs more memory. Here, we would leverage the user data to, one, perhaps pull the latest version of our code down from GitHub, start our application, and then leveraging the simple notification service, notify perhaps some monitoring system or the person on call that, hey, an instance has been launched and is now up and running and ready to go. So combining our launch configurations, multiple availability zones, and auto-scaling service, we can achieve a system that is not only highly available, but fault-tolerant and self-healing as well. Now let's talk about demand-based scaling. There are plenty of applications that receive varying loads of traffic. Web applications, APIs, corporate applications, and one of the keys to a resilient infrastructure within Amazon Web Services is the ability to be elastic, the ability to scale out to meet that demand when the demand is happening. So what we're looking at here is how we can leverage auto-scaling group and Amazon CloudWatch alarms to monitor. In this particular example, what we're going to monitor is the average aggregate CPU across all of the machines in this auto-scaling group. So what we're going to say is that when the aggregate average CPU of the auto-scaling group is above 80% for 5 minutes, at that time, when that particular threshold is breached, we want to trigger a scaling policy. Now that scaling policy will say we want to add 100% of the group. That means we're going to double the group. So we're going to go from 2 EC2 instances to 4 EC2 instances. And then we're going to wait 7 minutes before we do anything else. And that's considered our cooldown period. Now, the scaling policy, whether it's a scaling policy or a scheduled action, no matter how it's triggered, ultimately what that does is to update the setting on the auto-scaling group that we call the desired capacity. That is, how many instances do we want running right now? So again, our scaling policy in this example is going to add 100% of the group and then wait 7 minutes. So this 7 minutes is an important step. That cooldown period allows us to determine whether or not these new instances have indeed affected the aggregate CPU and brought it down underneath our threshold on which we set an alarm. If we don't have this, if we just launch it and then we immediately look to see, is the CPU still above 80%? Yes, okay, launch again. We would end up scaling out far too rapidly. We would end up with far too many servers than we really need. So it's important to adjust that cooldown period. If you have a period that's too short and you're not giving these new machines enough time to actually bootstrap and get to work, then you're going to end up scaling out far too fast. If you wait too long, then you could end up in a situation where you're scaling out too slow and your system is seeing these spikes of heavy load that aren't being addressed. So it's important to really tune your application and understand how long it really takes for these machines to bootstrap and become available. So that's scaling out based on demand. And in this example, we used CPU utilization, but you could very well scale based on network traffic, the amount of network packets that we're seeing come in, the amount of bandwidth that we're seeing going out. You could scale based on a custom metric, such as the number of processes that are running. It doesn't really matter. Whatever is the bottleneck for your particular application. So just as important as scaling out is scaling in. We need to scale out to meet demand. We need to scale in to save money. So a very similar example, in this case, we're going to have a second CloudWatch alarm that is monitoring, again, it's also monitoring the average aggregate CPU across all of the EC2 instances within our auto-scaling group. In this example, we're looking for the CPU utilization to fall below 40% for at least 5 minutes. So as soon as this threshold has been breached, again, we're going to trigger a scaling policy. In this example, we're going to remove 50% of the group. That means we're going to cut that group in half. We will go from 8 to 4, wait 7 minutes, give it that cooldown period. If after 7 minutes our CPU is still below 40%, then we will scale yet again and go from 4 to 2 machines. Now it's important to know, again, while we're changing the desired capacity, we do have a minimum and a maximum that we can set on the autoscaling group so that we will never go below a certain number of machines or go above a certain number of machines. So again, we want to set our minimum based on the minimum number of machines we need to meet the minimum load that we will ever see. And our maximum number of machines are most likely going to be determined by our budget. How many machines are we willing to pay for? So that's just one example of demand-based scaling. The possibilities are almost endless in putting these kinds of systems together, but those are just two examples of scaling horizontally, both out and in, based on demand. Now let's review a demo of creating an autoscaling group within Amazon EC2. From the AWS console dashboard, we're going to go back to EC2. I'm going to scroll down all the way to the bottom here to autoscaling. I'm going to click on autoscaling groups. From here, I'm going to click Create Autoscaling Group. Now, if you recall what we talked about earlier, we need two things are required. One, not just the autoscaling group, but also a launch configuration. The launch configuration specifies what is to be launched, and then the autoscaling group will define where that gets launched, the subnets, availability zones, and so on. So we're going to first create a new launch configuration before we can create the actual autoscaling group. I'm going to click Next. Now, from here, it's prompting me to choose the AMI, the Amazon machine image. I generally like to work with Amazon Linux, so I'm going to select that one. From here, I can select the type of EC2 instance. Again, for those of us that might be new to AWS, I would recommend that we take advantage of the free tier, so we can use the T2 Micro there. I'm going to click Next. We need to name this launch configuration. So again, I'm going to call it LC for launch configuration. The IAM role, I'm going to give it my application so that later I can come back and add permissions to that role if my application needs to reach other AWS services such as S3 and so on. So down here at the bottom, I have an opportunity to add user data, which could be a bash script. So I could do something like hashbang /bin/bash. Now this user data script will run as root, so we don't need to do any kind of sudo in there. It will already be executed as the root user. So I can say yum install -y httpd, and that will force the installation of Apache. So perhaps that's all I want to do, and then something else can come back and update that particular script. Or from here, the next line might be to check out some code and put it into the appropriate directories. So again, just as a reminder that user data is a really powerful way to bootstrap these machines, especially in an auto-scaled environment where machines are coming and going according to demand. We want machines to get up and running as quickly as possible without manual intervention, and user data is one of the keys to do that. For these machines, they will be behind a load balancer, so they don't need public IPs. I'm going to say no, don't do that. From here, I'm going to add storage, which we don't really need. The 8 gig root volume is enough. From the security group, I'm going to select an existing one. I'm going to choose the web server security group that we created earlier. And then I'm going to hit Review. It's warning us that we won't be able to shell in on port 22, but that's okay. I'm going to hit Continue. And that is a review of our launch configuration, which I can go ahead and hit Create. I'm going to make sure that we have the right key pair in place and acknowledge, yes, indeed, I do have that key pair on my local machine. So I'm going to hit Create that launch configuration. Now that our launch configuration is created, we can leverage that in our autoscaling group. So you can see here, the wizard has already populated this to use the launch configuration that we just created. I'm going to call the group, again, AWS Live Lessons ASG for autoscaling group. Let's just say we'll start with 2 instances, 1 per availability zone, and I'm going to choose both let's make sure that we have the right VPC, the 10.2, and I'm going to have this autoscaling group use both US East 2A and 2B. Now, normally in a production environment, we'd use all 3. So I could go here and create a new subnet. So let's just go ahead and do that real quick to make sure that we're using all 3 availability zones. So I'm going to create one called public B, put this one also in 10.2. Excuse me, you already have that one. Yep, public C, we're going to put this one in US East 2C. All right, so this one will be 10.2.20.24. We're going to go ahead and create that one. Now that we have that subnet created, we should be able to, let's refresh that. There we go. Here's our public C. So that's the appropriate way to do it. We want to leverage all 3 availability zones that are available to us in this region. Next, we'll configure our scaling policies. For the sake of this demo, we're just going to keep this one at its initial size. Let me go back there and make sure. Let's start with 3 instances, 1 per availability zone. I'm going to keep this. We're just going to maintain what we call a fixed fleet. We just want to maintain those 3 instances for now. Later, we can come back and configure scaling policies if we wanted to. Now we have the opportunity to create a notification. And here, if we wanted to, we could be notified of machines being terminated and machines being launched, and also receive notifications if there were any failures of those launches or terminations. So if we wanted to, we can add a notification. That would be the name of a topic that I've created, but I might want to create a topic. So from here, we could add notifications if we wanted to be notified of machines coming and going, machines being terminated or machines being scaled and replaced. So that would leverage the simple notification service. We're going to skip that for now and go on to tags. Again, common things like name, environment. In this particular case, I'm using the dev. And again, tagging is up to you, whatever makes the most sense to your business and organization and application. So there we go. We have our group name. We're going to maintain 3 instances. And we're going to hit create. And that's it. That's how you create an autoscaling group. We'll close that. And then we'll see here, you can see that this little eye icon means that something's happening. When you see that icon, you know that the autoscaling group is in the process of doing something. So we can go back here and look at the activity history and see that because we just created it, 3 instances are being launched. You can see that we desire 3, but we have 0 so far. If I hit refresh, you can see, there we go. Now our table shows us as having desired 3, and 3 are indeed running. Those 3 were successful, and we can click here and see these are the 3 instances that our autoscaling group created. If these instances were marked as being unhealthy, the autoscaling service will terminate those and replace them. So I'm going to go over here to details and show you that the health check type right now is set to EC2. So as long as the EC2 service says that these instances are healthy, then the autoscaling group will just leave them alone. As soon as something marks them as being unhealthy, then the autoscaling service will replace them. So let's go back here and see. Here's our 3 instances. They are considered to be in service. They are considered to be healthy. And so what I'm going to show you, just real quick, I'm going to click over into one of these instances. And from here, now we could use the command line tools to force this machine to be considered unhealthy. Or from here, we could just manually terminate that machine, which I'm going to do, just to show you how the autoscaling group will very quickly detect that something's wrong and replace that machine. So I'm going to hit terminate. Yes, terminate that machine. You can see it's shutting down, and before too long it will go into a terminated state. Doesn't take too long. And there we go. Our machine is now terminated. So if we come back over here to our autoscaling group and look at our activity history, if we refresh this, you'll see that the autoscaling group did notice that something was wrong. And you can see here at 24 seconds, it noticed something was wrong, and then 2 seconds later, it started launching a new instance. So it replaced that instance almost immediately. And so now we can go back and see, now that new instance is back in service and replaced. So that is autoscaling, maintaining a fixed fleet of 3 machines, balanced across all 3 availability zones, as you can see here, A, B, and C. So that is creating a launch configuration and an autoscaling group within Amazon EC2. So we're coming to the end of our time together, and I want to leave you with some overarching thoughts in regards to Amazon Web Services and a few notes about the Solutions Architect exam. Let's talk about the ideal within Amazon Web Services. The ideal infrastructure within Amazon Web Services can be described in a number of ways. One of them being that an ideal application is highly available. Now, that doesn't mean that it's never down. It just means that it's up a great majority of the time. So we have a number of services within Amazon Web Services that can help us achieve that. Those being the Amazon Machine Image, EC2 instances. We have, if we leverage services like S3 and RDS, which are inherently highly available, then that just adds to the high availability of our own service. We have autoscaling as well, which can replace failed instances. And again, high availability doesn't mean that it's never down. It just means that if there is some downtime, that it's kept to an absolute minimum. Now, fault tolerance, or an application that is fault tolerant, can help you achieve an application that is never down. So if there is a fault with one machine, we still have other machines in the background that can take up the slack and continue to handle traffic or meet demand, whatever it may be. And again, we have multiple EC2 instances. We should be leveraging multiple availability zones. We should be leveraging, in the case of applications that need to respond to TCP or HTTP type traffic, then we can leverage the elastic load balancer to help us achieve fault tolerance by spreading that traffic out among a number of machines, distributing that load, and that way if one fails, we still have multiple machines. We also want our systems within AWS to be secure. We have a number of services that can help with that as well. We have the AWS CLI and the console all operate on HTTPS. Every time we connect to the AWS API, that is done with SSL-enabled connections. We have a number of tools within our network, such as network access control lists, security groups, routing, multiple VPCs, VPN connections. We should be adding security within our application layers, right? Now remember that the operating system and applications are up to you. Those are your responsibility to ensure their security, but leveraging Amazon Machine Images, which are regularly published, we can stay on top of patch updates as far as our operating systems go. We also have access to the identity and access management service and policies. Remember that we want to grant least privilege and be rotating our keys, MFA, those kinds of things can all combine to help keep our environment and our applications secure. We also want our applications and our environment to be durable. We want our data to survive the loss of infrastructure, whether it's lost at a device level or an availability zone layer. We want to make sure that we have multiple copies of our data. And again, we can do that by leveraging systems like the Elastic Block Store and snapshots. So the Elastic Block Store is going to be inherently durable to the loss of a device, but by taking snapshots, those being stored in S3, and S3 being redundant across multiple availability zones, will give us a high degree of durability in our data. Also remember that we have the ability to copy snapshots, both EBS snapshots and RDS snapshots, to multiple regions, giving us a high degree of geographical diversity in our data. We also have Glacier. We also have the relational database service in multi-AZ deployments. If you're running systems in production using the relational database service, be sure to opt in to the multi-AZ deployment so that you have that secondary standby that can be failed over to in that situation where your primary becomes unreachable. Other aspects to an ideal environment would be that our systems are self-healing. Self-healing meaning that they fix faults on their own. And the keys to doing that are leveraging machine images that are pre-built with the software that you need, perhaps pre-configured to some degree, but leveraging user data. Remember, we have access to user data so that we can script our EC2 instances to get up and running, bootstrap them on first boot, and install what needs to be installed, configure what needs to be configured, and get that machine doing its job as quickly as possible. Combining the AMI with auto-scaling and user data is a really powerful system of self-healing. And I can speak from personal experience that these services, these tools have saved my life many times over the last 7 years. An ideal system would also be automated. We want to remove manual intervention. We want to remove the human error factor as much as possible. Humans are fallible creatures, and we become tired, we become grumpy, whatever it is, we're going to make mistakes. And so in things that need to happen regularly and over again, we don't want humans to get bored, we don't want them to get tired, so we want to automate these things. We want to leverage tools like AWS CloudFormation and auto-scaling and user data, perhaps Elastic Beanstalk and OpsWorks. We could even leverage Bash scripts or Python scripts or Node.js. The list goes on. The tools that Amazon Web Services gives us to create an automated environment are incredibly rich. There are so many options to choose from, and they make it so easy to create an environment that just does what it needs to do when it needs to do it. And last but not least, an important aspect of an environment within Amazon Web Services is also cost effective. So we want to pay for what you use, but use what you need and no more, right? So again, auto-scaling can help. We want to scale out to meet demand, scale in to save money. Be sure and leverage the EC2 reserved billing model for those applications and databases that are long-lived, that need to be running for long periods of time. For other things like batch processing, video transcoding, jobs that are very short or jobs that can tolerate being interrupted, be sure and leverage the spot market so that you can get EC2 instance at a fraction of the cost of the on-demand price. There is also what we call the Trusted Advisor, which is a tool that Amazon gives us that will automatically scan through our environment and point out areas that we can improve. It will tell us places that we can improve security, places we can improve performance. It will also point out ways that we can save money. It will tell you hey, you have an EBS volume sitting here not attached to an instance. Do you really want to be spending the money for that? As far as a cost-effective application or cost-effective infrastructure goes, some of that, a lot of it perhaps comes down to habits and practices. So be sure to clean up after yourself. Be sure to turn the lights off. When you're not using machines, do they really need to be running? So that's the ideal environment within Amazon Web Services. Now let's talk about best practices within Amazon Web Services. The first best practice is to design for failure. Amazon's CTO, Dr. Werner Vogels, is famous for saying, everything fails all the time. Now, it's not necessarily true. Amazon has built a system that is incredibly resilient and incredibly durable. You've heard me say this many times over. It's just important to remember that a lot of Amazon services are inherently highly available and fault tolerant. We should be always asking that question. What happens when this component fails? And we should include Amazon services in that. It's very rare and perhaps unlikely, but it's still possible for an Amazon service to be unavailable for whatever reason. So it's best practice when we start to architect a solution for a particular problem to start with the assumption that everything will fail eventually and assume that any component can fail at any time. And we're constantly asking, what happens when? What happens when our web server fails? We have more than one. We have several in multiple availability zones behind a load balancer. So if one fails, we have multiples that can pick up the slack. What happens when an availability zone is unreachable? We have multiple availability zones. What happens when an entire region is unavailable? It's very rare, but it could happen. We have to assume that it could happen. That's how we achieve a superior degree of high availability. So what happens when a region is unavailable? We can use Route 53, DNS, and multiple regions as disaster recovery to fail over to another region. Another best practice is to scale horizontally, to design our systems to be distributed. A lot of old school IT, a lot of old applications, especially those written throughout the 90s, were written with the idea that they would go to one server and that one server would be there for years on end. In those days, that was true. But we're operating in a different paradigm now. And I've seen a lot of organizations struggle with migrations because their applications were written to be monolithic and written to operate on one machine. So we have to think differently. We need to start scaling horizontally. We need to write our applications to be distributed. And so that means that our applications and our components should be stateless. If we do have an application that requires state, we should not be storing that state locally, but we should use things like Elasticache or DynamoDB. If we need to, we could rely on ELB sticky sessions as a way to help get our application migrated, but we should work to remove the need for that one. So again, our systems should be distributed and stateless. We should also be thinking of ways that we could parallelize and batch our work. So instead of one machine working on one job for 4 hours, is there a way we could break that job up so that 4 machines could get the same job done in 1 hour? In that example, it would cost the same amount of money, but it would be done in 1/4 of the time. We have other tools like Kinesis, Elastic MapReduce, and Lambda that can help with distributed processing. Some other best practices would be to think of our EC2 instances or resources as being disposable. This is especially true for EC2 instances. We're operating, again, from a very different paradigm. We are not on-premises data center or a co-location where we have a physical server in a rack that we expect to be there for a long period of time. We're not operating with fixed servers anymore. We're operating with virtual machines that could go away at any time. They could be terminated due to an accident, perhaps, an intern pushed the wrong button. Perhaps Amazon Web Services decides that this machine needs to be retired, or there is some kind of a problem with the physical infrastructure behind that EC2 instance and it just fails. We should be prepared for our machine to fail at any time and have things in place that can replace that. By thinking of our EC2 instances as being disposable, it means that if there's a problem, we just throw it away and start over and allow our automated processes to kick in and get that machine back to a usable state. By doing this, we can avoid configuration drift. Because EC2 instances are easily replaced, we don't have to worry about one machine being configured in one way, another machine being configured in another. We're not worried about shelling into that machine and ensuring that the right versions of software are installed. We can do that on one initial machine, create an Amazon machine image, and then roll that machine image out across the fleet, thereby ensuring that our entire fleet is configured in the same way. We could leverage configuration tools like OpsWorks, like Ansible, Chef, Puppet, and so on, Saltbox. We can leverage these tools to ensure that our fleet stays configured appropriately. And again, we should be thinking of these EC2 instances as disposable. Don't be afraid to throw them away and start over. If you've built your system right, you should be able to terminate a machine, watch it come back, pick up into the state that it's supposed to be in, and get back to work doing what it's supposed to do. And I can speak from personal experience that when you have a cluster of machines and you intentionally terminate one machine at a time and you see them roll over, it's very satisfying and it's a very exciting thing to see your infrastructure just heal itself and to see your infrastructure be replaced and come back into a usable state without a whole lot of manual intervention. And of course, automate, automate, automate. I cannot overemphasize that enough, that we want to get away from manual steps and manual intervention. Of course, in the beginning, there's going to be that manual steps to get these things in place. But ultimately, the state of nirvana that we're after is an environment that does what it needs to do based on one button press or based on a notification from CloudWatch alarms. So we have a number of tools that can help with that as well. Again, we have CloudFormation that can automate the creation, the management, and the deletion of very complex infrastructures. CloudFormation can help reproduce very complex infrastructures across numerous environments in numerous regions. We have Elastic Beanstalk and OpsWorks as well that can handle the underlying infrastructure for you. Again, as we've talked about, autoscaling and CloudWatch can help with the automation by automatically monitoring your environment and scaling out to meet demand, scaling in to save money. We have third-party tools available. Many of these have libraries and built-in support for Amazon Web Services. So tools like Ansible, Chef, and Puppet, and there are a number of others, but these seem to be the three most popular. So I would highly encourage you to look into these tools as ways to automate your environment. A few more best practices would be: one, security in layers. There's no one magic bullet for security. Security happens across a number of things within Amazon Web Services. We need security within our network, within our VPC, and we can use routes, NACLs, and security groups to make that happen. We need security at the account level, at the AWS API level, and we can do that leveraging the Identity and Access Management Service by creating the appropriate users, putting them in the appropriate groups, giving them least privilege, giving them enough privileges to do their job, but not so much as to be dangerous. We can leverage roles. We can apply roles to EC2 instances to other AWS services, cross-account roles to vendors and customers. And again, we can do that so that we can leverage temporary keys and avoid embedding or sharing long-lived keys. We do have access keys that are either on a per-user basis or temporary based on roles, and we want to be sure that if we transmit those, we do it in a secure way. And if in the case of long-lived credentials, like for an IAM user, we want to be sure to rotate those regularly. Be sure and leverage multiple accounts. Multiple accounts can help segregate between different environments like development, test, and production. You could segregate based on business unit, like finance has one, accounting has theirs, engineering has their account. And of course, as we talked about, protect that master account. Protect your master credentials at all costs. Enable MFA, lock that physical MFA key fob in a safe, and remember that companies have gone out of business because they did not protect their master account. The next best practice would be loose coupling. Loose coupling means that instead of writing a monolithic application, or instead of writing two applications that inherently know something about each other, instead of hard coding IP addresses, break that monolith up into microservices. Separate different services by using queues or messaging systems so they don't necessarily need inherent knowledge of each other. If they do, be sure to put load balancers between them so that you aren't hard coding IP addresses. Really look, if you're not already, be sure and look into the microservices architecture. It makes life a whole lot easier within Amazon Web Services. We should be writing our systems so that failures don't cascade. A failure in one service should be tolerated by another service. And we can achieve loose coupling by leveraging elastic load balancers. We can leverage queues within the Amazon Simple Queue service. We can achieve this via Kinesis Route 53 DNS so that we don't have to hard code, as I said, hard code IPs. We can leverage AWS Lambda as well as serverless infrastructure. And then, of course, last but not least, optimize for cost. Be sure and leverage those reserved instances, spot instances for short-running jobs, and of course, clean up after yourself and turn the lights off. There are plenty of cases where perhaps you're just running an experiment. If you don't clean that up, it's just going to sit there and continue to cost you money for something you're not using. In the case of development environments where your developers are working during normal business hours, 8 to 5, do we really need those development environments running at night? Do we need them running on the weekend? So look for opportunities to turn machines off. There are times when you might want to terminate some machines and other times when you want to stop machines but then turn them back on later. So those are our best practices within Amazon Web Services. Now let's talk about the exam for the Solutions Architect certification. For those of you looking to take the Solutions Architect exam, you can expect the exam to take approximately 80 minutes. You'll have somewhere around 55 questions. The exam is really good. The questions are worded in such a way as to test your ability to, one, gather the requirements and understand a technical challenge. From there, it tests your knowledge to actually architect a solution, to choose the solution that is most technically appropriate and cost-effective. The exam does a really good job of testing your knowledge of a number of different areas, including things like multi-tier architectures, distributed systems, elasticity and scalability, things like we've talked about with the elastic load balancer and auto-scaling. It tests your knowledge of networking within AWS. That would be VPCs, subnets, security groups, NACLs, route tables. It tests your knowledge of loose coupling and stateless systems, and also content delivery. From my experience, both having taken the exam and having worked with Amazon Web Services for the last 7 years, I can say that while this is not a comprehensive list of things that you need to know for the exam, I would say that if you're going to go on from here and study things in depth, these particular services are probably the most important services that you need to study and memorize and ingrain a lot of technical detail. And those would be the AWS Identity and Access Management, Amazon Elastic Compute Cloud, Amazon Virtual Private Cloud, Amazon Simple Storage Service, Amazon Elastic Block Store, Autoscaling, Elastic Load Balancing, and of course Amazon CloudWatch. There's more that you should go and study, but again, if I were to prioritize and point you to any that you should start with, it would be this list here. As you go forward, there are questions on the exam regarding cost effectiveness. As I mentioned, the exam does a good job of questioning your ability to choose solutions that are cost effective. So going forward in your studies, don't try to remember the dollar amounts that you pay, but remember what you pay for. So as an example, an EC2 instance might cost a certain dollar amount per hour. Don't try to remember all of those dollar amounts. Just try to remember that an EC2 instance costs a certain amount per hour. So not what you pay, but what you pay for. And of course, what I'll leave you with is that nothing beats hands-on experience. You can study and study and study, but nothing beats hands-on experience. So get out there and explore Amazon Web Services, build VPCs, launch EC2 instances, explore Amazon Kinesis, and get some hands-on experience. Cloud computing is still in its early days, and I believe Amazon Web Services is just getting started. My career over the last 7 years has been truly exciting, and I hope the same is true for you in the coming years as well. Thank you so much for joining me in this video series on Amazon Web Services. The concepts and technologies presented here will likely make even more sense when viewing these videos a second and third time, so I would highly encourage you to do so. From here, I would also encourage you to practice the hands-on labs available for free on the AWS website. As you move forward with your studies of AWS, remember that nothing beats hands-on experience, especially for those of you looking to take the Solutions Architect certification exam. So get out there, build VPCs, launch EC2 instances, explore AWS Lambda, Amazon Kinesis, and Amazon DynamoDB, and enjoy the wonderful world of cloud computing with Amazon Web Services.